1. Introduction to Mars. 1.1 History of Mars exploration. Mars, the fourth planet from the Sun, has captivated the imagination of humans for centuries. Its reddish appearance and proximity to Earth have made it a subject of fascination and curiosity. The history of Mars exploration is a testament to humanity's relentless pursuit of knowledge and the desire to uncover the mysteries of the universe. The earliest recorded observations of Mars can be traced back to ancient civilizations such as the Egyptians, Babylonians, and Greeks. These early astronomers observed the planet's motion across the night sky and noted its distinct red color. However, it wasn't until the invention of the telescope in the 17th century that scientists could begin to study Mars in more detail. In the late 19th century, the Italian astronomer Giovanni Schiaparelli made a significant contribution to the understanding of Mars. He observed a network of linear features on the planet's surface, which he called canali, meaning channels in Italian. This term was later mistranslated as canals, leading to speculation about the possibility of intelligent life on Mars. This sparked a wave of interest in Mars and set the stage for future exploration. The first successful mission to Mars was carried out by the Soviet Union in 1960. The spacecraft, named Martian 1, was intended to fly by Mars and gather data about the planet's atmosphere and magnetic field. Unfortunately, the mission failed, and it wasn't until 1964 that the Soviet Union achieved its first successful Mars flyby with the spacecraft Mariner 3. The United States entered the race to explore Mars with the Mariner program in the 1960s. Mariner 4, launched in 1964, became the first spacecraft to capture close-up images of Mars. The images revealed a barren and cratered landscape, dispelling the notion of a lush and inhabited planet. This marked a turning point in our understanding of Mars and paved the way for future missions. In the following decades, both the United States and the Soviet Union launched numerous missions to Mars, each building upon the knowledge gained from previous endeavors. These missions included flybys, orbiters, landers, and rovers, each designed to study different aspects of the planet. One of the most significant milestones in Mars exploration was the Viking program, launched by NASA in the 1970s. The Viking landers successfully touched down on the Martian surface and conducted experiments to search for signs of life. Although the results were inconclusive, the Viking missions provided valuable data about the planet's soil composition and atmospheric conditions. In recent years, technological advancements have allowed for more ambitious missions to Mars. The Mars Pathfinder mission, launched in 1996, deployed the Sojourner rover, the first successful Mars rover. This marked the beginning of a new era of robotic exploration, with subsequent missions such as the Mars Exploration Rover's Spirit and Opportunity, and the Curiosity rover, further expanding our knowledge of the Martian surface. In addition to robotic missions, there have been several attempts to send humans to Mars. The most notable of these is NASA's Mars Exploration Program, which aims to send astronauts to Mars in the 2030s. This ambitious endeavor poses numerous challenges, including the long-duration space travel, radiation exposure, and the need for self-sustaining habitats on the Martian surface. The history of Mars exploration is a testament to human ingenuity and the relentless pursuit of knowledge. Each mission has brought us closer to understanding the Red Planet and has paved the way for future exploration. As technology continues to advance, our understanding of Mars will undoubtedly deepen, and the dream of sending humans to Mars may soon become a reality. 1.2 Physical characteristics of Mars. Mars, often referred to as the Red Planet, is the fourth planet from the Sun in our solar system. It is a terrestrial planet with a rocky surface, similar to Earth. In this section, we will explore the physical characteristics of Mars, including its size, composition, and geological features. 1.2.1 Size and mass. Mars has a diameter of approximately 6,779 kilometers, 4,212 miles, which is about half the size of Earth. Its mass is roughly 10% that of Earth, making it significantly less massive. Due to its smaller size, Mars has a lower gravitational pull compared to Earth. The surface gravity on Mars is about 38% of Earth's gravity, which means that objects and individuals on Mars would weigh less than they do on Earth. 1.2.2 Composition. The composition of Mars is similar to that of Earth, primarily consisting of silicate rocks and metals. However, Mars has a thinner crust compared to Earth. The Martian crust is composed of basalt, a type of volcanic rock, and contains various minerals such as feldspar and olivine. The planet's core is believed to be made up of iron, nickel, and sulfur. One of the most distinctive features of Mars is its reddish color, which is due to the presence of iron oxide, also known as rust, on its surface. The iron oxide gives the planet its characteristic reddish hue and is responsible for its nickname, the Red Planet. 1.2.3 Surface features. Mars is known for its diverse and intriguing surface features. The planet is home to the largest volcano in the solar system, Olympus Mons, which stands at a staggering height of 22 kilometers (13.6 miles). This shield volcano is 3 times taller than Mount Everest, the highest peak on Earth. Mars also boasts the longest canyon in the solar system, Valles Marineris, which stretches over 4,000 kilometers (2,500 miles) in length. The surface of Mars is covered in a variety of geological formations, including impact craters, lava plains, and ancient riverbeds. These features provide evidence of a dynamic past, suggesting that Mars was once a more geologically active planet. The presence of dried-up river channels and ancient lake beds indicates that liquid water once flowed on the Martian surface, raising questions about the possibility of past or even present life on the planet. 1.2.4 Atmosphere. The atmosphere of Mars is much thinner than that of Earth, with a surface pressure about 0.6% of Earth's atmospheric pressure. It is primarily composed of carbon dioxide, 95.3%, with traces of nitrogen, 2.7%, and argon, 1.6%. The thin atmosphere on Mars means that it cannot retain heat as effectively as Earth's atmosphere, resulting in extreme temperature variations. The average temperature on Mars is around -63 degrees Celsius, -81 degrees Fahrenheit, but it can drop as low as -143 degrees Celsius, -225 degrees Fahrenheit, at the poles during the winter season. Despite the frigid temperatures, Mars experiences seasons similar to Earth due to its axial tilt. However, the Martian seasons are approximately twice as long as Earth's due to its longer orbit around the Sun. 1.2.5 Polar ice caps. Mars has polar ice caps at both its north and south poles. These ice caps are composed of a mixture of water ice and frozen carbon dioxide, also known as dry ice. During the Martian winter, a significant portion of the atmosphere condenses and freezes onto the polar ice caps, causing them to expand. As the seasons change and temperatures rise, the ice caps partially sublimate, releasing gases back into the atmosphere. The polar ice caps on Mars are of great interest to scientists as they provide valuable information about the planet's climate history and the potential availability of water resources. The presence of water ice on Mars raises the possibility of utilizing these resources for future human missions, such as extracting water for drinking, growing crops, and producing rocket propellant. In conclusion, Mars is a fascinating planet with unique physical characteristics. Its size, composition, surface features, atmosphere, and polar ice caps all contribute to its distinctiveness. Understanding these physical characteristics is crucial for planning and executing successful missions to Mars, as well as for unraveling the mysteries of the planet's past and its potential for supporting life. 1.3 Atmosphere and climate of Mars. Mars, often referred to as the Red Planet, has long captivated the imagination of scientists and space enthusiasts alike. One of the key factors that make Mars so intriguing is its unique atmosphere and climate. In this section, we will explore the composition of the Martian atmosphere, its weather patterns, and the challenges it presents for human exploration. 1.3.1 Composition of the Martian atmosphere. The atmosphere of Mars is significantly different from that of Earth. It is composed mainly of carbon dioxide, CO2, with traces of nitrogen, N2, argon, Ar, and small amounts of oxygen, O2, carbon monoxide, CO, and water vapor, H2O. The thin atmosphere of Mars is approximately 100 times less dense than Earth's atmosphere, making it inhospitable for human life as we know it. The presence of carbon dioxide in the Martian atmosphere has important implications for the planet's climate. It acts as a greenhouse gas, trapping heat and contributing to the warming of the planet. However, due to the thin atmosphere, the greenhouse effect on Mars is much weaker than on Earth, resulting in significantly colder temperatures. 1.3.2 Weather patterns on Mars. Despite its thin atmosphere, Mars experiences a variety of weather phenomena. The planet's axial tilt and elliptical orbit around the Sun cause seasonal changes, similar to Earth. However, the extreme differences in atmospheric density and composition led to some unique weather patterns on Mars. Dust storms are a common occurrence on Mars and can vary in scale from small, localized storms to planet-wide events. These storms can last for weeks or even months, engulfing the entire planet in a haze of dust. The dust particles in the atmosphere can have a significant impact on the planet's climate, affecting temperature and sunlight penetration. Another interesting weather phenomenon on Mars is the occurrence of water ice clouds. These clouds form at high altitudes and are composed of water vapor freezing into ice crystals. They can create stunning visual displays, with wispy formations and iridescent colors. The presence of water ice clouds indicates the potential for water vapor in the Martian atmosphere, which is crucial for future human exploration and potential colonization. 1.3.3 Temperature and climate. The average temperature on Mars is much colder than on Earth, with an average surface temperature of around -80 degrees Fahrenheit, -62 degrees Celsius. However, temperatures can vary significantly depending on the location and time of year. During the Martian winter, temperatures can plummet to -195 degrees Fahrenheit, -125 degrees Celsius near the poles. The thin atmosphere of Mars also means that the planet experiences extreme temperature fluctuations between day and night. During the day, temperatures can reach a relatively mild -20 degrees Fahrenheit, -29 degrees Celsius, near the equator, while at night, they can drop to a bone-chilling -100 degrees Fahrenheit, -73 degrees Celsius. The climate on Mars is predominantly dry and arid, with very little precipitation. However, recent discoveries have indicated the presence of water ice beneath the surface, particularly in the polar regions. This discovery has sparked excitement among scientists, as it suggests the possibility of accessing water resources for future human missions. 1.3.4 Challenges for human exploration. The unique atmosphere and climate of Mars present significant challenges for human exploration and colonization. The thin atmosphere offers little protection from harmful solar radiation, which can be detrimental to human health. The extreme cold temperatures and lack of breathable air make it necessary for astronauts to rely on advanced life support systems and protective suits to survive. The presence of dust storms also poses a challenge for human missions. These storms can reduce visibility, interfere with communication systems, and potentially damage equipment. Strategies for mitigating the impact of dust storms, such as designing robust structures and developing advanced dust mitigation technologies, are crucial for the success of future Mars missions. Understanding the atmosphere and climate of Mars is essential for planning and executing successful missions to the planet. Scientists and engineers continue to study and analyze data from Mars missions to gain a deeper understanding of the planet's weather patterns, temperature variations, and atmospheric composition. This knowledge will be invaluable in designing spacecraft, habitats, and life support systems that can withstand the harsh Martian environment. In the next section, we will delve into the potential for life on Mars and explore the ongoing search for signs of past or present microbial life on the red planet. 1.4 Potential for life on Mars. The question of whether life exists or has ever existed on Mars has fascinated scientists and researchers for decades. Mars, often referred to as the red planet, has long been considered a prime candidate for harboring extraterrestrial life due to its similarities to Earth and the presence of water in its past. In this section, we will explore the potential for life on Mars and the ongoing efforts to search for signs of past or present life. 1.4.1 The search for life. The search for life on Mars began with the first missions to the planet in the 1960s. Early spacecraft, such as the Mariner and Viking missions, focused on studying the planet's surface and atmosphere for any signs of life. While these missions did not find conclusive evidence of life, they provided valuable insights into the planet's geology and climate. Since then, our understanding of Mars has greatly expanded, and new missions have been launched to explore the planet in more detail. The Mars rovers, such as Spirit, Opportunity, and Curiosity, have been instrumental in gathering data about the planet's past and present conditions. These rovers have discovered evidence of ancient lakes, riverbeds, and even organic molecules, suggesting that Mars may have once been a habitable environment. 1.4.2 Habitability of Mars. To determine the potential for life on Mars, scientists study the planet's habitability. Habitability refers to the conditions necessary for life to exist, such as the presence of water, a stable climate, and the availability of essential elements and nutrients. One of the key factors in determining habitability is the presence of liquid water. While Mars is currently a cold and dry planet, evidence suggests that liquid water may have existed in the past. The discovery of ancient riverbeds and the presence of ice caps at the planet's poles indicate that Mars had a more hospitable climate billions of years ago. Another important consideration is the availability of essential elements for life, such as carbon, nitrogen, and phosphorus. Mars has been found to contain these elements, as well as other compounds necessary for life, such as sulfur and hydrogen. The presence of these elements suggests that Mars may have had the building blocks necessary for life to develop. 1.4.3 Extremophiles and life in extreme environments. On Earth, scientists have discovered life forms known as extremophiles that can survive in extreme environments. These organisms have adapted to thrive in conditions that would be inhospitable to most other life forms, such as high temperatures, acidic environments, or extreme pressure. The discovery of extremophiles has expanded our understanding of the potential for life on other planets, including Mars. If life exists on Mars, it is likely to be microbial in nature, similar to extremophiles found on Earth. These microorganisms could potentially survive in the harsh conditions of the Martian environment, such as the low temperatures, thin atmosphere, and high levels of radiation. 1.4.4 Martian meteorites and biosignatures. In addition to studying Mars directly, scientists have also examined Martian meteorites that have landed on Earth. These meteorites provide valuable insights into the geological history of Mars and may contain evidence of past life. One such meteorite, known as ALH 84001, gained significant attention in the 1990s when scientists claimed to have found fossilized remains of ancient Martian bacteria within it. While the findings were controversial and have not been universally accepted, they sparked further interest in the search for life on Mars. Scientists continue to analyze Martian meteorites for any potential biosignatures, such as organic compounds or isotopic ratios that could indicate the presence of life. These studies, combined with ongoing missions to Mars, are helping to build a more comprehensive picture of the planet's potential for life. 1.4.5 Future missions and the search for life. The search for life on Mars is far from over. Future missions, such as the Mars Sample Return mission, aim to bring back samples from the Martian surface for detailed analysis on Earth. These samples could provide definitive evidence of past or present life on Mars. Additionally, upcoming missions, such as the Mars 2020 rover and the ExoMars mission, will continue to explore the planet's habitability and search for signs of life. These missions will employ advanced instruments and technologies to study the Martian environment in unprecedented detail. While the question of whether life exists on Mars remains unanswered, the ongoing exploration and research efforts are bringing us closer to finding the answer. Whether we discover microbial life or evidence of past life, the implications would be profound, as it would demonstrate that life can exist beyond Earth and open up new possibilities for future human exploration and colonization of Mars. In the next chapter, we will delve into the planning and preparation required for a mission to Mars, including the goals and objectives of such a mission, the challenges and risks involved, and the selection of astronauts for the journey. 2. Mission planning. 2.1 Goals and objectives of a Mars mission. A mission to Mars is a monumental undertaking that requires careful planning and consideration of its goals and objectives. The primary goal of a Mars mission is to explore and understand the Red Planet, unravel its mysteries, and pave the way for future human exploration and potential colonization. This chapter will delve into the various goals and objectives that drive a Mars mission, highlighting the scientific, technological, and human aspects of such an endeavor. 2.1.1 Scientific exploration. One of the primary objectives of a Mars mission is to conduct scientific exploration of the planet. Mars is a fascinating world with a unique geological history and potential for past or present life. By studying its geology, geography, atmosphere, and climate, scientists hope to gain insights into the formation and evolution of planets, including Earth. Mars provides a natural laboratory for understanding the processes that shape terrestrial planets and the potential for habitability beyond our own planet. Exploring Mars also offers the opportunity to search for signs of past or present life. Scientists are eager to investigate whether Mars once harbored microbial life or if it still does today. By studying the planet's surface, subsurface, and atmosphere, scientists hope to find evidence of organic molecules, water, and other essential ingredients for life. Such discoveries would have profound implications for our understanding of the origin and prevalence of life in the universe. 2.1.2 Technological advancement. A Mars mission serves as a catalyst for technological advancement in various fields. From spacecraft design and propulsion systems to life support and communication technologies, the challenges of a Mars mission push the boundaries of human ingenuity and innovation. Developing and testing new technologies for long-duration space travel, resource utilization, and planetary exploration not only benefit future Mars missions but also have practical applications on Earth. For instance, advancements in propulsion systems for interplanetary travel can lead to more efficient and sustainable methods of transportation on Earth. The development of life support systems for long-duration missions can have applications in remote and extreme environments on our own planet. The communication and navigation systems required for Mars missions can enhance global communication networks and improve disaster response capabilities. 2.1.3 Human exploration and colonization. Another significant objective of a Mars mission is to pave the way for human exploration and potential colonization of the planet. Sending humans to Mars would be a historic achievement, expanding our presence beyond Earth and opening up new possibilities for the future of humanity. By establishing a sustainable human presence on Mars, we can learn to live and work in a harsh and alien environment, developing the necessary technologies and infrastructure for long-term habitation. The challenges of a Mars mission, such as radiation exposure, limited resources, and isolation, provide valuable lessons for future human space exploration. By overcoming these challenges, we can develop the knowledge and capabilities needed for longer missions to other destinations in our solar system, such as the moons of Jupiter and Saturn or even beyond. Ultimately, the goal is to establish a permanent human presence on Mars, creating a second home for humanity and ensuring the long-term survival of our species. 2.1.4 International collaboration. A Mars mission is a complex and resource-intensive endeavor that requires international collaboration and cooperation. No single nation has the resources or expertise to undertake such a mission alone. International collaboration not only shares the burden of costs and resources but also brings together the best minds and talents from around the world, fostering scientific and technological advancements on a global scale. Collaboration in a Mars mission promotes diplomatic relations, strengthens international partnerships, and fosters a sense of unity and shared purpose among nations. It also ensures that the benefits of Mars exploration, such as scientific discoveries and technological advancements, are shared by all of humanity. By working together, nations can pool their resources, knowledge, and expertise to achieve common goals and overcome the challenges of exploring and colonizing Mars. In conclusion, the goals and objectives of a Mars mission encompass scientific exploration, technological advancement, human exploration, and international collaboration. By exploring and understanding Mars, we gain insights into the formation and evolution of planets, search for signs of life, and push the boundaries of human knowledge and capabilities. A Mars mission serves as a stepping stone for future human exploration and potential colonization, while also fostering international collaboration and cooperation. The journey to Mars is not just a scientific and technological endeavor, it is a testament to human curiosity, ingenuity, and the indomitable spirit of exploration. 2.2 Mission architecture and design. The successful execution of a mission to Mars requires careful planning and meticulous design of the mission architecture. Mission architecture refers to the overall strategy and framework that guides the design and implementation of a Mars mission. It encompasses various aspects such as spacecraft design, trajectory planning, crew selection, and mission objectives. In this section, we will explore the key considerations and components of mission architecture and design for a journey to Mars. 2.2.1 Mission objectives. Before embarking on a mission to Mars, it is crucial to define clear and achievable objectives. These objectives serve as the guiding principles for the entire mission and shape the design of the spacecraft, crew selection, and scientific experiments. The primary objective of a Mars mission is often to explore and study the planet's geology, atmosphere, and potential for life. Additionally, missions may aim to test new technologies, demonstrate human capabilities in space exploration, or pave the way for future colonization efforts. 2.2.2 Mission Phases. A Mars mission typically consists of several distinct phases, each with its own set of challenges and requirements. These phases include the launch and trans-Mars injection, interplanetary cruise, arrival and landing on Mars, surface operations, and the return journey. Each phase requires careful planning and coordination to ensure the success and safety of the mission. 2.2.3 Spacecraft Design. The design of the spacecraft is a critical aspect of mission architecture. The spacecraft must be capable of withstanding the harsh conditions of space and providing a safe and habitable environment for the crew during the long-duration mission. It must also be equipped with the necessary propulsion systems, life support systems, communication and navigation systems, and scientific instruments. The spacecraft design must strike a balance between functionality, efficiency, and safety. 2.2.4 Crew Selection. Selecting the right astronauts for a Mars mission is a complex process. The crew must possess a diverse range of skills and expertise, including scientific knowledge, engineering skills, and the ability to work effectively in a team under extreme conditions. They must also undergo rigorous physical and psychological evaluations to ensure their ability to withstand the physical and mental challenges of a long-duration space mission. The crew selection process considers factors such as health, adaptability, problem-solving skills, and compatibility with other crew members. 2.2.5 Mission Duration and Sustainability. A mission to Mars involves a significant amount of time spent in space, with the entire mission lasting several years. Mission architects must carefully consider the duration of the mission and plan for the sustainability of the crew and spacecraft during this extended period. This includes provisions for food, water, waste management, and healthcare. Additionally, the mission must be designed to minimize the reliance on Earth for resupply and support, as the distance and communication delays make it impractical for constant assistance. 2.2.6 Trajectory Planning. The trajectory of the spacecraft plays a crucial role in determining the duration and efficiency of the mission. Mission architects must carefully calculate the optimal trajectory that minimizes fuel consumption while ensuring a safe and timely arrival at Mars. This involves considering factors such as launch windows, gravitational assists from other celestial bodies, and the alignment of Earth and Mars in their respective orbits. Trajectory planning is a complex task that requires precise calculations and simulations to ensure a successful mission. 2.2.7 Risk Mitigation and Contingency Planning. Mars missions are inherently risky endeavors, and mission architects must develop robust risk mitigation strategies and contingency plans. This involves identifying potential risks and developing backup systems and procedures to address them. Mission architects must consider risks such as equipment failures, medical emergencies, radiation exposure, and the psychological well-being of the crew. Contingency plans should include provisions for emergency repairs, medical interventions, and alternative mission objectives in case of unforeseen circumstances. 2.2.8 International Collaboration. Mars missions are complex and resource-intensive endeavors that often require international collaboration. Mission architects must consider the benefits of collaboration, including shared expertise, resources, and costs. International collaboration can also foster diplomatic relations and promote scientific cooperation. However, it also presents challenges such as coordinating different national interests, technical standards, and legal frameworks. Mission architects must navigate these complexities to ensure successful collaboration and mission execution. In conclusion, mission architecture and design are crucial components of a Mars mission. The design of the spacecraft, trajectory planning, crew selection, and risk mitigation strategies all play a vital role in the success and safety of the mission. By carefully considering these factors and addressing the challenges associated with a journey to Mars, mission architects can pave the way for future exploration and potentially the colonization of the Red Planet. 2.3 Selection of astronauts for Mars mission. Selecting the right astronauts for a mission to Mars is a crucial and complex process. The journey to Mars is a long and arduous one, lasting several months, and the astronauts will be living and working in a confined and isolated environment for an extended period of time. Therefore, it is essential to carefully choose individuals who possess the necessary skills, physical and mental health, and the ability to work effectively as a team. 2.3.1 Physical and mental health. One of the primary considerations in selecting astronauts for a Mars mission is their physical and mental health. The astronauts must be in excellent physical condition, as they will be subjected to the rigors of space travel and the challenges of living in a reduced gravity environment. They must undergo rigorous medical examinations to ensure that they are free from any underlying health conditions that could be exacerbated during the mission. In addition to physical health, mental health is also of utmost importance. The astronauts will be facing long periods of isolation and confinement, which can have a significant impact on their psychological well-being. They must possess the mental resilience and emotional stability to cope with the challenges and stresses of living in a confined space for an extended period of time. Psychological evaluations and assessments are conducted to identify individuals who are psychologically fit for the mission. 2.3.2 Skills and Expertise. Astronauts selected for a Mars mission must possess a diverse range of skills and expertise. They should have a strong background in science, engineering, and technology, as they will be conducting scientific experiments, maintaining and repairing equipment, and troubleshooting any technical issues that may arise during the mission. They should also have a solid understanding of the principles of spaceflight and be able to adapt to the unique challenges of living and working in a microgravity environment. In addition to technical skills, astronauts must also possess excellent communication and teamwork abilities. They will be part of a small team, living in close quarters for an extended period of time, and it is crucial that they can work effectively together and resolve conflicts in a constructive manner. Leadership skills are also important, as they may be required to take charge in emergency situations or make critical decisions during the mission. 2.3.3 Training and Preparation. Preparing astronauts for a mission to Mars requires extensive training and preparation. Astronauts undergo a rigorous training program that includes physical fitness training, simulated spacewalks, and emergency response drills. They are trained in various scientific disciplines, including geology, biology, and atmospheric science, to enable them to conduct meaningful research on Mars. Astronauts also receive training in spacecraft systems, including navigation, life support, and communication systems. They learn how to operate and maintain the various equipment and systems on board the spacecraft, as well as how to respond to any technical malfunctions or emergencies that may arise during the mission. Furthermore, astronauts undergo training in survival skills and contingency planning. They learn how to handle medical emergencies, perform basic medical procedures, and provide first aid to themselves and their crewmates. They also receive training in psychological resilience and stress management techniques to help them cope with the challenges of long-duration space travel. 2.3.4 Team Composition and Diversity. The composition of the astronaut team for a Mars mission is carefully considered to ensure a balance of skills, expertise, and personalities. It is important to have a diverse team that can bring different perspectives and problem-solving approaches to the mission. This diversity can enhance the team's ability to adapt to unexpected challenges and find innovative solutions. The team should ideally consist of individuals with complementary skills and expertise, such as scientists, engineers, medical professionals, and pilots. Each member should be able to contribute to the mission objectives and work collaboratively with others. The team should also be able to function well under stress and maintain a positive and supportive atmosphere throughout the mission. 2.3.5 Selection Process. The selection process for astronauts for a Mars mission is rigorous and highly competitive. It typically involves multiple stages, including written applications, interviews, medical evaluations, and psychological assessments. Candidates are evaluated based on their qualifications, skills, experience, and personal attributes. The selection committee considers factors such as academic and professional achievements, leadership potential, teamwork abilities, and adaptability to the challenges of space travel. They also assess the candidate's motivation and commitment to the mission, as well as their ability to communicate effectively and inspire others. The final selection is made based on a combination of objective criteria and subjective judgment. The goal is to assemble a team of highly qualified and capable individuals who can successfully accomplish the mission objectives and represent humanity on the journey to Mars. In conclusion, the selection of astronauts for a mission to Mars is a meticulous process that takes into account various factors, including physical and mental health, skills and expertise, training and preparation, team composition, and diversity. The chosen astronauts must possess the necessary qualifications, abilities, and personal attributes to successfully undertake the challenges of a Mars mission. Their selection is a critical step in ensuring the success and safety of the mission, as well as inspiring future generations of explorers. 2.4 Challenges and Risks of a Mars Mission. A mission to Mars is an ambitious and complex undertaking that presents numerous challenges and risks. The journey to the Red Planet is fraught with difficulties, and the astronauts who embark on this mission must be prepared to face a wide range of obstacles. In this section, we will explore some of the major challenges and risks associated with a Mars mission. 2.4.1 Distance and Duration. One of the primary challenges of a Mars mission is the vast distance between Earth and Mars. On average, Mars is approximately 225 million kilometers away from Earth. This means that a one-way journey to Mars can take anywhere from 6 to 9 months, depending on the alignment of the planets. The long duration of the journey poses several risks to the crew, including exposure to cosmic radiation, muscle and bone loss due to microgravity, and psychological stress from isolation and confinement. 2.4.2 Radiation exposure. During the journey to Mars, astronauts are exposed to high levels of radiation from cosmic rays and solar flares. Unlike Earth, Mars does not have a protective magnetic field or a thick atmosphere to shield astronauts from these harmful radiation sources. Prolonged exposure to radiation can increase the risk of cancer, damage DNA, and impair the functioning of vital organs. To mitigate this risk, spacecraft must be equipped with radiation shielding materials, and astronauts must follow strict protocols to minimize their exposure. 2.4.3 Microgravity effects. Another significant challenge of a Mars mission is the prolonged exposure to microgravity. Microgravity can have detrimental effects on the human body, including muscle and bone loss, cardiovascular deconditioning, and changes in the immune system. Astronauts must undergo rigorous physical exercise routines and receive regular medical checkups to counteract these effects. Additionally, the long-term effects of microgravity on human health are still not fully understood, making it crucial to conduct extensive research and monitoring during the mission. 2.4.4 Life Support Systems. Maintaining a sustainable life support system is vital for the success of a Mars mission. Astronauts will need a constant supply of oxygen, water, and food throughout their journey and stay on Mars. Developing reliable and efficient life support systems that can operate in the harsh Martian environment is a significant technical challenge. Recycling and reusing resources, such as water and air, will be crucial to minimize the reliance on resupply missions from Earth. 2.4.5 Psychological and social factors. The isolation and confinement experienced by astronauts during a Mars mission can have profound psychological effects. Being away from family and friends for an extended period, living in a confined space, and dealing with the challenges and uncertainties of the mission can lead to feelings of loneliness, depression, and anxiety. Maintaining the mental well-being of the crew will be essential, and psychological support systems, such as regular communication with loved ones and access to counseling services, must be in place. 2.4.6 Landing and surface operations. The landing and surface operations on Mars present significant risks to the crew and the success of the mission. Landing on Mars is a complex and high-stakes maneuver that requires precise navigation and control. The Martian atmosphere is much thinner than Earth's, making it challenging to slow down the spacecraft during descent. Once on the surface, astronauts will face the harsh Martian environment, including extreme temperatures, dust storms, and potential exposure to toxic chemicals. Ensuring the safety of the crew during landing and surface operations will require meticulous planning, robust engineering, and contingency measures. 2.4.7 Communication and navigation. Maintaining communication with Earth and accurate navigation during a Mars mission is crucial for the safety and success of the mission. The vast distance between Mars and Earth introduces significant communication delays, ranging from a few minutes to over 20 minutes, depending on the relative positions of the planets. This delay can hinder real-time decision-making and emergency response. Developing advanced communication and navigation systems that can operate reliably over long distances and in challenging Martian conditions is a critical challenge that must be overcome. 2.4.8 Technical failures and contingency planning. Space missions are inherently risky, and technical failures can occur despite meticulous planning and preparation. Equipment malfunctions, system failures, or unforeseen events can jeopardize the mission and the safety of the crew. Developing robust contingency plans and redundancy systems is essential to mitigate the risks associated with technical failures. Astronauts must also receive extensive training in emergency procedures and problem-solving to handle unexpected situations. In conclusion, a mission to Mars presents numerous challenges and risks that must be carefully addressed and mitigated. From the long duration of the journey to the risks of radiation exposure, microgravity effects, and psychological stress, astronauts will face a multitude of obstacles. However, with careful planning, technological advancements, and a comprehensive understanding of the risks involved, a successful Mars mission is within our reach. 3. Spacecraft and technology. 3.1 Spacecraft design and components. Spacecraft design and components play a crucial role in the success of a mission to Mars. The journey to Mars is a complex and challenging endeavor that requires careful planning and engineering. In this section, we will explore the various aspects of spacecraft design and the components that make up these advanced vehicles. 3.1.1 Spacecraft design. Designing a spacecraft for a mission to Mars involves a combination of engineering expertise, scientific knowledge, and innovative thinking. The spacecraft must be able to withstand the harsh conditions of space, including extreme temperatures, radiation, and the vacuum of space. It must also be capable of carrying the necessary equipment, supplies, and crew members for the duration of the mission. One of the key considerations in spacecraft design is weight. Every kilogram of mass that is launched into space requires a significant amount of fuel, making it essential to minimize the weight of the spacecraft. Engineers use lightweight materials and advanced construction techniques to achieve this goal. Another important aspect of spacecraft design is aerodynamics. During the launch phase, the spacecraft must be able to withstand the intense forces and vibrations experienced during liftoff. The shape of the spacecraft is carefully designed to minimize drag and maximize stability during ascent. Furthermore, the spacecraft must be equipped with advanced navigation and communication systems to ensure accurate trajectory calculations and real-time communication with mission control on Earth. These systems allow for precise course corrections and enable the crew to stay in constant contact with ground support. 3.1.2 Spacecraft components. A spacecraft consists of various components that work together to ensure the success of the mission. Let's take a closer look at some of the key components. 3.1.2.1 Propulsion system. The propulsion system is responsible for providing the necessary thrust to propel the spacecraft from Earth to Mars. There are different types of propulsion systems used in interplanetary missions, including chemical rockets, ion propulsion, and nuclear propulsion. Each system has its advantages and disadvantages in terms of efficiency, thrust, and fuel requirements. 3.1.2.2 Power generation and storage. Spacecraft require a reliable source of power for their systems and instruments. Solar panels are commonly used to generate electricity from the sun's energy. These panels are designed to be highly efficient and lightweight. The generated power is stored in batteries or fuel cells to provide electricity during periods of low sunlight or when the spacecraft is in shadow. 3.1.2.3 Life support systems. Life support systems are crucial for sustaining the crew during the long-duration mission to Mars. These systems provide the crew with breathable air, clean water, and a controlled environment to live and work in. They also remove carbon dioxide, regulate temperature and humidity, and manage waste products. Advanced technologies, such as closed-loop systems and regenerative life support, are employed to maximize efficiency and minimize resource consumption. 3.1.2.4 Communication and navigation systems. Communication and navigation systems are essential for maintaining contact with mission control and accurately navigating the spacecraft. These systems include antennas, transmitters, receivers, and data processing units. They enable the crew to communicate with Earth, receive commands, and transmit scientific data back to mission control. Precise navigation is crucial for achieving the correct trajectory and ensuring a successful landing on Mars. 3.1.2.5 Scientific instruments and payloads. Spacecraft are equipped with a wide range of scientific instruments and payloads to study the Martian environment. These instruments include cameras, spectrometers, seismometers, and drills, among others. They are designed to collect data on the geology, atmosphere, climate, and potential for life on Mars. The data collected by these instruments is crucial for advancing our understanding of the red planet and determining its habitability. 3.1.3 Future developments. As technology continues to advance, spacecraft design and components will continue to evolve. Future missions to Mars may see the development of more efficient propulsion systems, lightweight and durable materials, and advanced life support systems. Additionally, advancements in robotics and artificial intelligence may lead to the integration of autonomous systems in spacecraft, reducing the need for human intervention during certain mission phases. In conclusion, spacecraft design and components are integral to the success of a mission to Mars. Engineers and scientists work together to design spacecraft that can withstand the harsh conditions of space and carry out the necessary scientific investigations. As we continue to explore the red planet, advancements in technology will drive the development of more advanced and capable spacecraft, paving the way for future missions and the eventual colonization of Mars. 3.2 Propulsion systems for interplanetary travel. Interplanetary travel to Mars is a complex and challenging endeavor that requires advanced propulsion systems to overcome the vast distances and gravitational forces involved. The propulsion systems used for interplanetary travel must be capable of providing the necessary thrust to propel spacecraft from Earth to Mars and back, while also ensuring the safety and well-being of the crew during the long-duration missions. Chemical propulsion systems. Chemical propulsion systems have been the primary means of propulsion for interplanetary missions to date. These systems rely on the combustion of chemical propellants to generate thrust. The most commonly used chemical propulsion system is the liquid rocket engine, which uses liquid propellants such as liquid oxygen (LOX) and liquid hydrogen (LH2), or a combination of liquid oxygen and liquid kerosene (RP1). Liquid rocket engines offer high thrust and efficiency, making them suitable for launch and initial stages of the journey. However, they have limitations in terms of specific impulse, which is a measure of the efficiency of a propulsion system. Chemical propulsion systems have relatively low specific impulse compared to other propulsion technologies, which limits their effectiveness for long-duration missions. Electric propulsion systems. Electric propulsion systems, also known as ion propulsion systems, offer a more efficient alternative to chemical propulsion for interplanetary travel. These systems use electric power to accelerate and expel charged particles, typically xenon ions, at high velocities to generate thrust. Electric propulsion systems have significantly higher specific impulse compared to chemical propulsion systems, making them ideal for long-duration missions. One of the most commonly used electric propulsion systems is the Hall effect thruster. This system uses a magnetic field to accelerate ions and generate thrust. Hall effect thrusters offer high specific impulse and low fuel consumption, making them suitable for interplanetary travel. However, they have relatively low thrust, which limits their use for launch and initial stages of the journey. Nuclear propulsion systems. Nuclear propulsion systems have long been considered as a potential solution for interplanetary travel due to their high specific impulse and potential for long-duration missions. These systems use the energy released from nuclear reactions to heat a propellant, such as liquid hydrogen, and expel it at high velocities to generate thrust. One type of nuclear propulsion system is the nuclear thermal rocket, NTR, which uses a nuclear reactor to heat the propellant. NTRs offer high specific impulse and thrust, making them suitable for both launch and interplanetary travel. However, they have challenges related to the safety and containment of nuclear materials, which need to be addressed before their practical implementation. Another type of nuclear propulsion system is the nuclear electric propulsion, NEP, which uses a nuclear reactor to generate electricity that powers an electric propulsion system. NEPs offer high specific impulse and fuel efficiency, making them ideal for long-duration missions. However, they have lower thrust compared to NTRs, which limits their use for launch and initial stages of the journey. Solar sail propulsion systems. Solar sail propulsion systems offer a unique and innovative approach to interplanetary travel. These systems use large, lightweight sails that harness the momentum of photons from the sun to generate thrust. Solar sails do not require propellants and offer unlimited propulsion potential as long as sunlight is available. Solar sails offer high specific impulse and fuel efficiency, making them suitable for long-duration missions. However, they have relatively low thrust, which limits their use for launch and initial stages of the journey. Additionally, the effectiveness of solar sails decreases as the distance from the sun increases, which poses challenges for interplanetary missions. Hybrid propulsion systems. Hybrid propulsion systems combine different propulsion technologies to overcome the limitations of individual systems and optimize performance for interplanetary travel. These systems often use a combination of chemical propulsion for launch and initial stages of the journey, and electric or nuclear propulsion for the interplanetary cruise. By utilizing the strengths of different propulsion technologies, hybrid systems can achieve high thrust during launch and initial stages, and high specific impulse and fuel efficiency during the interplanetary cruise. This approach allows for more efficient and effective interplanetary travel, reducing the overall mission duration and improving crew safety and well-being. In conclusion, interplanetary travel to Mars requires advanced propulsion systems that can overcome the challenges of vast distances and gravitational forces. Chemical propulsion systems have been the primary means of propulsion for interplanetary missions, but electric, nuclear, solar sail, and hybrid propulsion systems offer more efficient and effective alternatives for long-duration missions. The development and implementation of these propulsion technologies are crucial for the success of future Mars missions and the exploration of other celestial bodies in our solar system. 3.3 Life support systems for long-duration missions. Life support systems are crucial for the success of long-duration missions to Mars. These systems are responsible for providing astronauts with the necessary resources and conditions to sustain life in the harsh and inhospitable environment of space. As humans venture further into space, the development of advanced life support systems becomes increasingly important to ensure the health and well-being of astronauts during their journey to Mars and their stay on the Red Planet. 3.3.1 Oxygen generation and carbon dioxide removal. One of the primary functions of a life support system is to generate oxygen for the crew to breathe. On Earth, we have an abundant supply of oxygen in the atmosphere, but in space, it is necessary to produce oxygen through other means. One method is through the electrolysis of water, where water molecules are split into hydrogen and oxygen using an electric current. This process not only generates oxygen for the crew but also provides a source of hydrogen for fuel. Another important aspect of life support systems is the removal of carbon dioxide, which is exhaled by the crew. High levels of carbon dioxide can be harmful to humans, so it is essential to maintain a safe and breathable atmosphere inside the spacecraft or habitat. Carbon dioxide removal systems, such as molecular sieves or amine-based systems, are used to absorb and remove carbon dioxide from the air, ensuring a healthy environment for the crew. 3.3.2 Water recycling and waste management. Water is a precious resource in space, and it is essential to recycle and reuse as much water as possible to minimize the need for resupply missions. Life support systems incorporate water recycling technologies that purify and filter wastewater, including urine and sweat, to produce clean drinking water. These systems use processes like distillation, filtration, and ion exchange to remove impurities and contaminants, ensuring a sustainable water supply for the crew. Waste management is another critical aspect of life support systems. Astronauts produce solid waste, such as food scraps and packaging, as well as liquid waste, including urine and other bodily fluids. Advanced waste management systems are designed to safely store and process these wastes, minimizing the risk of contamination and ensuring a clean and hygienic living environment for the crew. Some waste management systems even utilize microbial processes to convert organic waste into useful resources, such as nutrients for plant growth. 3.3.3 Food production and nutrition. During long-duration missions to Mars, it is not feasible to rely solely on pre-packaged food from Earth. Therefore, life support systems include provisions for food production and cultivation. Hydroponics and aeroponics systems are commonly used to grow plants in a controlled environment, using nutrient-rich water or mist instead of soil. These systems allow astronauts to cultivate fresh fruits, vegetables, and herbs, providing them with a nutritious and varied diet. Food production in space also involves the cultivation of microorganisms, such as algae and bacteria, which can be used as a source of protein and other essential nutrients. These microorganisms can be grown in bioreactors and harvested for consumption by the crew. Additionally, advancements in 3D printing technology have enabled the creation of food items using edible materials and nutrient-rich powders, providing astronauts with a wider range of food options. 3.3.4 Temperature and humidity control. Maintaining a comfortable and stable environment inside the spacecraft or habitat is crucial for the well-being of the crew. Life support systems incorporate temperature and humidity control mechanisms to regulate the climate and prevent extreme fluctuations. Heating and cooling systems, as well as humidity control devices, are used to maintain optimal conditions for the crew, ensuring their comfort and preventing the growth of mold or other harmful microorganisms. 3.3.5 Radiation protection. One of the major challenges of long-duration space missions is the exposure to high levels of radiation. In deep space, astronauts are exposed to cosmic rays and solar radiation, which can have detrimental effects on their health. Life support systems include radiation shielding materials, such as lead or polyethylene, to minimize the exposure of the crew to harmful radiation. Additionally, monitoring systems are in place to continuously measure radiation levels and alert the crew in case of any significant increase in radiation. 3.3.6 Psychological support. Living in isolation and confinement for extended periods can have a significant psychological impact on astronauts. Life support systems also address the psychological well-being of the crew by providing adequate support and resources. Communication systems, both with mission control and with family and friends on Earth, are crucial for maintaining social connections and reducing feelings of isolation. Additionally, recreational activities, such as virtual reality simulations, exercise equipment, and entertainment systems, are provided to help astronauts relax and cope with the challenges of living in a confined space. In conclusion, life support systems play a vital role in ensuring the success and safety of long-duration missions to Mars. These systems provide astronauts with the necessary resources, including oxygen, water, and food, while also maintaining a comfortable and healthy living environment. As we continue to explore and colonize space, the development of advanced life support technologies will be crucial in enabling humans to thrive in the challenging conditions of space and on other celestial bodies. 3.4.1 Communication systems. Communication between Earth and Mars is essential for the success of any mission. The communication systems used must be reliable, efficient, and capable of transmitting data over long distances. One of the primary methods of communication is through the use of radio waves. Radio signals are transmitted from Earth to Mars and vice versa, allowing for the exchange of information between the two planets. To establish communication, large antennas are used on both Earth and Mars. These antennas are designed to transmit and receive radio signals with high precision. The Deep Space Network (DSN), operated by NASA, is a network of antennas located around the world that enables continuous communication with spacecraft in deep space, including those on their way to Mars. The communication systems on Mars missions also include onboard transmitters and receivers. These systems are responsible for transmitting data collected by the spacecraft's instruments back to Earth and receiving commands from mission control. The data is typically transmitted in the form of digital signals, which are encoded and modulated to ensure accurate transmission. In addition to radio communication, future missions to Mars may also explore the use of laser communication systems. Laser communication has the potential to provide higher data rates and more efficient communication compared to traditional radio waves. However, laser communication systems are still in the experimental stage and require further development before they can be used in practical missions. 3.4.2 Navigation systems. Accurate navigation is crucial for spacecraft traveling to Mars. The navigation systems used must be able to determine the spacecraft's position, velocity, and orientation with high precision. This information is essential for trajectory corrections, course adjustments, and ensuring a safe and accurate landing on Mars. One of the primary navigation systems used is the Deep Space Network's Doppler and ranging measurements. By measuring the Doppler shift in the radio signals transmitted between Earth and the spacecraft, mission control can determine the spacecraft's velocity relative to Earth. Ranging measurements, on the other hand, involve measuring the time it takes for a signal to travel between Earth and the spacecraft, allowing for the calculation of the spacecraft's distance from Earth. In addition to the Deep Space Network's measurements, spacecraft traveling to Mars also rely on onboard navigation systems. These systems use sensors such as star trackers, sun sensors, and inertial measurement units to determine the spacecraft's orientation and position relative to the stars and the Sun. By combining these measurements with data from the Deep Space Network, mission control can accurately track the spacecraft's trajectory and make any necessary course corrections. During the entry, descent, and landing phase, navigation becomes even more critical. To ensure a safe landing on Mars, spacecraft use a combination of radar and imaging systems to determine their altitude, velocity, and position relative to the Martian surface. These systems provide real-time data that allows for precise control of the landing process, ensuring a successful touchdown on the Red Planet. 3.4.3 Future developments. As technology continues to advance, communication and navigation systems for Mars missions are expected to improve. Researchers and engineers are constantly exploring new technologies and techniques to enhance the reliability and efficiency of these systems. One area of research is the development of advanced communication protocols and coding techniques. These advancements aim to increase the data rates and improve the error correction capabilities of communication systems, allowing for faster and more reliable transmission of data between Earth and Mars. Another area of focus is the development of autonomous navigation systems. These systems would enable spacecraft to navigate and make course corrections without relying on constant communication with Earth. By using onboard sensors and advanced algorithms, spacecraft could autonomously determine their position and make necessary adjustments to their trajectory, reducing the reliance on ground control. Furthermore, the use of artificial intelligence (AI) and machine learning algorithms is being explored to improve navigation and communication systems. AI can help optimize communication protocols, predict and mitigate signal interference, and enhance the accuracy of navigation calculations. These advancements have the potential to revolutionize the way we communicate with and navigate spacecraft on missions to Mars. In conclusion, communication and navigation systems are vital components of any mission to Mars. The ability to establish reliable communication and accurately navigate the vast distances between Earth and Mars is crucial for the success of these missions. With ongoing advancements in technology, we can expect to see even more efficient and robust communication and navigation systems in future missions, paving the way for further exploration and discovery on the Red Planet. 3.5 Robotic exploration of Mars. Robotic exploration has played a crucial role in our understanding of Mars. Before humans can set foot on the Red Planet, robotic missions serve as our eyes and ears, providing valuable data and paving the way for future human exploration. These missions have allowed us to study the Martian environment, search for signs of life, and gather information about the planet's geology, atmosphere, and climate. 3.5.1 Early robotic missions. The exploration of Mars began with the first successful flyby mission, Mariner 4, in 1965. This mission provided the first close-up images of the Martian surface, revealing a barren and cratered landscape. Since then, numerous robotic missions have been sent to Mars, each with its own set of objectives and scientific instruments. One of the most significant early missions was the Viking program, consisting of 2 landers and 2 orbiters, which successfully landed on Mars in 1976. The Viking landers conducted experiments to search for signs of life, analyze the soil composition, and study the Martian weather. Although the results were inconclusive regarding the presence of life, the Viking missions provided valuable insights into the Martian environment. 3.5.2 Rovers, exploring the Martian surface. One of the most remarkable achievements in robotic exploration of Mars has been the deployment of rovers. These mobile robots have revolutionized our understanding of the Martian surface by allowing us to explore different regions and conduct detailed scientific investigations. The Sojourner rover, part of the Mars Pathfinder mission in 1997, was the first successful Mars rover. It provided valuable data on the composition of Martian rocks and soil, as well as the planet's weather patterns. Following the success of Sojourner, NASA's Mars Exploration Rover (MER) mission, consisting of the rovers Spirit and Opportunity, was launched in 2003. These rovers exceeded their planned mission duration and provided valuable insights into the geological history of Mars, including evidence of past water activity. In 2012, NASA's Mars Science Laboratory mission successfully landed the car-sized rover Curiosity on Mars. Curiosity has been exploring the Gale crater, studying the planet's geology, climate, and potential habitability. It has made significant discoveries, including evidence of ancient lakes and the presence of organic molecules, further fueling the search for signs of past or present life on Mars. 3.5.3 Sample return missions. While rovers have been instrumental in exploring the Martian surface, they have limitations in terms of the amount of data they can collect and the distance they can cover. To overcome these limitations, the concept of sample return missions has gained traction. A sample return mission involves collecting samples of Martian soil, rocks, or atmosphere and bringing them back to Earth for detailed analysis. This would allow scientists to study the samples using advanced laboratory techniques that are not possible on Mars. NASA and the European Space Agency (ESA) have been working on a joint mission called Mars Sample Return (MSR). The mission would involve multiple spacecraft working together to collect, store, and return samples from Mars. The plan includes a rover that would collect samples and place them in a cache, a lander that would retrieve the cache and launch it into Mars orbit, and an orbiter that would capture the sample container and bring it back to Earth. The successful completion of a sample return mission would be a significant milestone in Mars exploration, as it would provide scientists with pristine Martian samples to study in detail. These samples could potentially hold clues about the planet's past, including the possibility of ancient life. 3.5.4 Future robotic missions. The exploration of Mars through robotic missions is far from over. Several upcoming missions are planned to further our understanding of the Red Planet. NASA's Mars 2020 mission, scheduled for launch in 2022, will deploy the Perseverance rover. This rover will search for signs of past microbial life, collect samples for future return to Earth, and test technologies for future human missions. The European Space Agency's ExoMars mission, consisting of the Rosalind Franklin rover and the Kazakh lander, is also planned for launch in the near future. The mission aims to search for signs of past or present life, study the planet's subsurface, and investigate the Martian atmosphere. In addition to these missions, private companies and other space agencies around the world are also planning their own robotic missions to Mars. These missions will continue to push the boundaries of our knowledge and pave the way for future human exploration. Robotic exploration of Mars has been instrumental in expanding our understanding of the Red Planet. From early flyby missions to the deployment of rovers and the prospect of sample return missions, these robotic missions have provided valuable data and insights into the Martian environment. As we continue to explore Mars, robotic missions will play a crucial role in preparing for future human missions and unraveling the mysteries of this fascinating planet. 3.6 Sample return missions. Sample return missions are an essential component of Mars exploration. These missions aim to collect samples from the Martian surface and bring them back to Earth for detailed analysis. The scientific value of studying Martian samples on Earth cannot be overstated. They provide invaluable insights into the planet's geology, climate history, potential for life, and much more. In this section, we will explore the challenges and strategies involved in planning and executing sample return missions. 3.6.1 Importance of sample return missions. Sample return missions hold immense scientific significance. While robotic missions have provided us with a wealth of information about Mars, they are limited in their ability to conduct detailed analysis on the planet's surface. By bringing back samples to Earth, scientists can utilize a wide range of sophisticated laboratory techniques that are not currently available on Mars. These samples can reveal the composition of Martian rocks and minerals, providing clues about the planet's geological history. By studying the isotopic ratios of certain elements, scientists can determine the age of these rocks and gain insights into the timing of geological events on Mars. Additionally, the presence of certain minerals or organic compounds could indicate the past or present existence of life on the planet. Furthermore, studying Martian samples can help scientists understand the potential habitability of Mars for future human missions. By analyzing the samples for signs of water, nutrients, and other essential resources, researchers can assess the feasibility of sustaining human life on the planet. 3.6.2 Challenges of sample return missions. Sample return missions are complex and challenging endeavors. They require precise planning, advanced technology, and careful consideration of various factors. Some of the key challenges involved in sample return missions include 3.6.2.1 Sample collection. Collecting samples from the Martian surface is a delicate process. The samples must be carefully selected to ensure they represent a diverse range of geological features and potential habitats for life. Robotic rovers or landers equipped with specialized tools, such as drills and scoops, are used to collect the samples. The samples are then sealed in airtight containers to prevent contamination and degradation during the return journey. 3.6.2.2 Sample contamination. Maintaining the integrity of the collected samples is of utmost importance. Contamination from Earth organisms could compromise the scientific value of the samples. Special precautions are taken to ensure that the sample collection and handling equipment is thoroughly sterilized before it comes into contact with the Martian surface. Cleanrooms and strict protocols are employed to minimize the risk of contamination. 3.6.2.3 Sample retrieval and launch. Once the samples are collected and sealed, they need to be safely retrieved and launched back into space. This requires a carefully orchestrated sequence of events, including the rendezvous of the sample container with the return vehicle, the transfer of the samples, and the successful launch from the Martian surface. The return vehicle must have the capability to safely carry the samples back to Earth without compromising their integrity. 3.6.2.4 Interplanetary transit. The journey back to Earth from Mars is a long and complex one. The return vehicle must navigate the vast distances of interplanetary space, accounting for gravitational forces and orbital dynamics. The samples must be protected from the harsh space environment, including radiation and extreme temperatures, to ensure their preservation during the transit. 3.6.2.5 Re-entry and landing on Earth. The final phase of a sample return mission involves the re-entry and landing of the return vehicle on Earth. The vehicle must withstand the intense heat and forces of re-entry, and its descent and landing must be carefully controlled to ensure the safety of the samples. Once landed, the samples are transported to a specialized facility where they can be analyzed under controlled conditions. 3.6.3 Sample return mission strategies. To overcome the challenges associated with sample return missions, various strategies have been proposed and studied. One approach is the direct return strategy, where a single mission is designed to collect and return the samples in a single trip. This approach minimizes the complexity and cost of multiple missions but requires a larger and more capable return vehicle. Another strategy is the sample caching approach, where multiple missions are conducted to collect and cache samples on Mars. These samples are then retrieved and returned to Earth by a subsequent mission. This approach allows for more flexibility in sample collection and reduces the risk of sample loss during the return journey. Additionally, international collaboration plays a crucial role in sample return missions. Sharing resources, expertise, and costs among multiple space agencies can enhance the success and efficiency of these missions. Collaborative efforts, such as the Mars Sample Return Campaign led by NASA and ESA, aim to bring together the collective capabilities of different nations to achieve the ambitious goal of returning Martian samples to Earth. In conclusion, sample return missions are vital for advancing our understanding of Mars. By bringing back samples from the Martian surface, scientists can conduct detailed analysis and unlock the secrets of the Red Planet. Despite the challenges involved, ongoing research and international collaboration are paving the way for future sample return missions, which will undoubtedly contribute to our knowledge of Mars and its potential for life. 4. Journey to Mars. 4.1 Launch and Trans-Mars injection. The journey to Mars begins with the launch of the spacecraft from Earth. This critical phase of the mission requires careful planning and execution to ensure a successful departure from our planet's gravitational pull. Once the spacecraft is in orbit, it undergoes a series of maneuvers to achieve the necessary trajectory for a trans-Mars injection. 4.1.1 Launching into orbit. Launching a spacecraft into orbit is a complex and precise process. It involves the ignition of powerful rocket engines that generate enough thrust to overcome Earth's gravity and propel the spacecraft into space. The launch vehicle, typically a powerful rocket, carries the spacecraft and provides the necessary thrust to reach the desired orbit. During the launch, the spacecraft experiences intense vibrations and acceleration forces. To protect the delicate instruments and systems on board, the spacecraft is designed to withstand these harsh conditions. The launch vehicle follows a predetermined flight path, known as the ascent trajectory, to ensure a safe and efficient ascent into orbit. 4.1.2 Achieving Trans-Mars Injection. Once the spacecraft reaches its initial orbit around Earth, it is ready for the next crucial step, the trans-Mars injection. This maneuver involves firing the spacecraft's propulsion system to increase its velocity and change its trajectory, aiming to intersect with Mars' orbit. The timing of the trans-Mars injection is crucial, as it depends on the relative positions of Earth and Mars in their respective orbits around the Sun. Mission planners carefully calculate the optimal launch window, taking into account the positions of the two planets and the energy required to transfer the spacecraft from Earth to Mars. To achieve the trans-Mars injection, the spacecraft's propulsion system, often powered by chemical rockets, is ignited for a specific duration. The engines generate a thrust that propels the spacecraft on a trajectory that will intersect with Mars' orbit. The duration and direction of the burn are precisely calculated to ensure the spacecraft is on the correct trajectory. During the trans-Mars injection, the spacecraft undergoes a series of trajectory correction maneuvers to refine its path and ensure a precise rendezvous with Mars. These maneuvers are crucial to account for any deviations from the planned trajectory caused by factors such as gravitational forces from other celestial bodies or slight errors in the initial burn. 4.1.3 Challenges and Considerations. The launch and trans-Mars injection phase of a mission to Mars presents several challenges and considerations that must be addressed to ensure a successful journey. One of the primary challenges is the immense distance between Earth and Mars. The average distance between the two planets is about 225 million kilometers, 140 million miles. This vast distance means that the spacecraft must travel for several months, depending on the alignment of the planets, before reaching Mars. During this time, the spacecraft and its crew are exposed to the harsh conditions of space, including radiation and microgravity. Another critical consideration is the limited payload capacity of the launch vehicle. The spacecraft must carry all the necessary supplies, equipment, and fuel for the entire mission, including the return journey. Mission planners must carefully optimize the payload to ensure that essential systems and scientific instruments are included while minimizing unnecessary weight. Additionally, the trans-Mars injection maneuver requires precise calculations and timing. Any errors in the burn duration or direction could result in the spacecraft missing its target or encountering significant challenges during the journey. Mission planners and engineers work together to develop accurate trajectory models and propulsion systems capable of executing the necessary maneuvers. Furthermore, the spacecraft's propulsion system must be reliable and capable of providing the necessary thrust for the trans-Mars injection. Redundancy and backup systems are often incorporated to mitigate the risk of propulsion system failures during this critical phase of the mission. In conclusion, the launch and trans-Mars injection phase of a mission to Mars is a complex and challenging endeavor. It requires careful planning, precise calculations, and reliable propulsion systems to ensure a successful departure from Earth and a trajectory that will lead the spacecraft to its destination. Despite the challenges, advancements in space technology and mission planning have made it possible for us to embark on this incredible journey of exploration and discovery. 4.2 Interplanetary Cruise and Trajectory. Once the spacecraft has successfully launched from Earth and completed the trans-Mars injection, it enters the interplanetary cruise phase of the mission. This phase is a critical and lengthy part of the journey to Mars, as it can take several months to reach the red planet. During this time, the spacecraft must navigate through the vastness of space, following a carefully calculated trajectory to ensure a successful arrival at Mars. 4.2.1 Calculating the trajectory. The trajectory of a spacecraft on its journey to Mars is determined by a combination of factors, including the position of Earth and Mars in their respective orbits, the desired arrival time, and the available propulsion systems. Mission planners and engineers work together to calculate the most efficient trajectory that minimizes fuel consumption while ensuring a safe and timely arrival. To calculate the trajectory, scientists use complex mathematical models and computer simulations. They take into account the gravitational forces exerted by the Sun, Earth, and Mars, as well as the spacecraft's velocity and direction. By carefully analyzing these variables, they can plot a course that will allow the spacecraft to reach Mars with the least amount of fuel and time. 4.2.2 Hohmann Transfer Orbit. The most common trajectory used for interplanetary missions, including those to Mars, is known as the Hohmann Transfer Orbit. This trajectory takes advantage of the relative positions of Earth and Mars in their orbits around the Sun. It involves launching the spacecraft from Earth's orbit and placing it on a trajectory that intersects with Mars' orbit. The Hohmann Transfer Orbit is an elliptical path that allows the spacecraft to use the gravitational pull of both Earth and Mars to its advantage. By carefully timing the launch and the spacecraft's velocity, engineers can ensure that the spacecraft will arrive at Mars when the planet is at the closest point to its orbit around the Sun, known as the opposition. 4.2.3 Gravity Assist Maneuvers. In addition to the Hohmann Transfer Orbit, mission planners often utilize gravity assist maneuvers to further optimize the trajectory of the spacecraft. A gravity assist maneuver involves using the gravitational pull of a planet or moon to alter the spacecraft's trajectory and increase its velocity. During the interplanetary cruise phase, the spacecraft may encounter other celestial bodies, such as Venus or Earth's moon. By carefully timing the spacecraft's approach and utilizing the gravitational pull of these bodies, engineers can adjust the trajectory and increase the spacecraft's speed. This allows for a more efficient journey to Mars, as less fuel is required to reach the desired destination. 4.2.4 Communication and Navigation. Maintaining communication and accurate navigation during the interplanetary cruise phase is crucial for the success of the mission. The vast distances between Earth and Mars pose challenges for real-time communication, as the signals can take anywhere from a few minutes to over 20 minutes to travel one way. To overcome this challenge, mission planners establish a network of deep space communication antennas on Earth, strategically positioned to ensure continuous communication with the spacecraft. These antennas receive and transmit signals to the spacecraft, allowing for the exchange of data, commands, and scientific observations. Navigation during the interplanetary cruise phase relies on a combination of onboard sensors, star trackers, and radio signals from Earth. The spacecraft's position and velocity are constantly monitored and adjusted to ensure it remains on the correct trajectory. Mission control teams on Earth work closely with the spacecraft's onboard systems to ensure accurate navigation and course corrections if necessary. 4.2.5 Crew Activities and Health. During the interplanetary cruise phase, the crew members on board the spacecraft have important tasks to perform to ensure their well-being and readiness for the upcoming mission on Mars. They undergo regular physical exercise to counteract the effects of microgravity and maintain their muscle and bone strength. Mental health support is also provided, as the long duration of the journey can be psychologically challenging. The crew members also engage in scientific research and experiments, taking advantage of the unique environment of deep space. They may study the effects of long-duration space travel on the human body, conduct experiments related to the mission's objectives, and contribute to the overall scientific knowledge of space exploration. Regular communication with mission control and their loved ones on Earth is essential for the crew's morale and mental well-being. Video conferences and email exchanges allow them to stay connected with their families and receive updates on the progress of the mission. Conclusion. The interplanetary cruise phase of a mission to Mars is a critical and complex part of the journey. Calculating the trajectory, utilizing gravity assist maneuvers, maintaining communication and navigation, and ensuring the well-being of the crew are all essential components of a successful mission. As technology advances and our understanding of space travel improves, future missions to Mars will continue to refine and optimize these aspects, paving the way for further exploration and potential colonization of the Red Planet. 4.3 Radiation Protection during the journey. Radiation is one of the most significant challenges that astronauts will face during a journey to Mars. Unlike Earth, Mars does not have a protective magnetic field or a thick atmosphere to shield astronauts from harmful radiation. As a result, astronauts will be exposed to higher levels of radiation during their journey to and from Mars, as well as during their stay on the Martian surface. Therefore, it is crucial to develop effective radiation protection measures to ensure the health and safety of the crew. 4.3.1 Understanding radiation in space. Before discussing radiation protection measures, it is important to understand the nature of radiation in space. Space radiation consists of high-energy particles, such as protons and heavy ions, which are emitted by the Sun and other celestial bodies. These particles can penetrate spacecraft materials and human tissues, causing damage to cells and DNA. The two main sources of radiation in space are solar particle events, SPECE, and galactic cosmic rays, GCRs. SPECE are short-duration bursts of high-energy particles that occur during solar flares or coronal mass ejections. These events can release a large amount of radiation in a short period of time, posing a significant risk to astronauts. GCRs, on the other hand, are high-energy particles that originate from outside our solar system. They are more constant in nature and pose a long-term radiation hazard during interplanetary travel. 4.3.2 Shielding the spacecraft. One of the primary methods of protecting astronauts from radiation is through spacecraft shielding. The spacecraft itself can act as a barrier, reducing the amount of radiation that reaches the crew. Shielding materials, such as aluminum, polyethylene, and water, can effectively attenuate radiation by absorbing or scattering the particles. The thickness and composition of the shielding material are crucial factors in determining its effectiveness. However, adding too much shielding material can increase the weight of the spacecraft, making it more challenging and costly to launch. Therefore, a balance must be struck between providing adequate protection and maintaining a manageable spacecraft mass. Advanced materials and innovative designs are being explored to develop lightweight yet effective shielding solutions for future Mars missions. 4.3.3 Monitoring and early warning systems. In addition to spacecraft shielding, monitoring and early warning systems play a crucial role in radiation protection. Continuous monitoring of radiation levels inside the spacecraft can provide real-time data on the radiation environment and help astronauts take appropriate measures to minimize their exposure. This can be achieved through the use of dosimeters, which are devices that measure the absorbed dose of radiation. Early warning systems can alert the crew about the occurrence of solar particle events, giving them time to seek shelter in shielded areas of the spacecraft. These systems rely on space-based observatories, such as the Solar and Heliospheric Observatory, SOHO, and the Advanced Composition Explorer, ACE, which monitor the Sun and provide data on solar activity. Timely warnings can enable astronauts to take necessary precautions and reduce their radiation exposure. 4.3.4 Biological countermeasures. In addition to spacecraft shielding and monitoring, biological countermeasures can help mitigate the effects of radiation on astronauts. These countermeasures aim to protect and repair the DNA and cells damaged by radiation. One approach is to develop pharmaceutical interventions that can enhance the body's natural defense mechanisms against radiation. For example, certain drugs and antioxidants have shown promise in reducing the harmful effects of radiation on the body. Another approach is to explore the use of genetic modification techniques to enhance the radiation resistance of astronauts. By modifying specific genes involved in DNA repair and radiation response, scientists hope to create astronauts who are more resilient to the effects of radiation. However, ethical considerations and long-term effects of genetic modifications need to be carefully evaluated before implementing such strategies. 4.3.5 Behavioral and operational measures. In addition to technological solutions, behavioral and operational measures can also contribute to radiation protection during the journey to Mars. For example, mission planners can optimize the trajectory of the spacecraft to minimize the exposure to radiation hotspots. By carefully selecting the launch window and trajectory, astronauts can avoid regions of space with high radiation levels, such as the South Atlantic anomaly. Furthermore, astronauts can be trained to adopt radiation protection practices, such as spending less time in high-risk areas of the spacecraft and using shielding materials during periods of increased radiation. Regular exercise and maintaining a healthy lifestyle can also help mitigate the effects of radiation on the body. These behavioral and operational measures, combined with technological solutions, can significantly reduce the radiation risks associated with a journey to Mars. In conclusion, radiation protection is a critical aspect of planning a mission to Mars. The absence of a protective magnetic field and a thin atmosphere on Mars poses significant challenges in ensuring the health and safety of astronauts. Through spacecraft shielding, monitoring systems, biological countermeasures, and behavioral measures, scientists and engineers are working towards developing effective radiation protection strategies. By addressing this challenge, we can pave the way for successful human exploration and colonization of Mars. 4.4 Maintaining crew health and well-being. As astronauts embark on the long and arduous journey to Mars, one of the most critical aspects of the mission is ensuring the health and well-being of the crew. The physical and psychological challenges of space travel, combined with the harsh conditions of the Martian environment, make it essential to have comprehensive measures in place to maintain crew health throughout the mission. 4.4.1 Physical fitness and exercise. Maintaining physical fitness is crucial for astronauts during their journey to Mars. Extended periods of weightlessness can lead to muscle atrophy and bone loss, making regular exercise a necessity. On board the spacecraft, astronauts will have access to exercise equipment specially designed for use in microgravity. These include treadmills, resistance training devices, and stationary bicycles. Regular exercise routines will help astronauts counteract the effects of weightlessness and maintain muscle strength and bone density. 4.4.2 Nutritional requirements. Proper nutrition is vital for crew members to stay healthy and perform at their best during the mission. A balanced diet that provides all the necessary nutrients, vitamins, and minerals will be carefully planned and prepared for the astronauts. The food will be specially formulated to meet the unique challenges of space travel, including long shelf life, lightweight packaging, and minimal waste generation. Additionally, efforts will be made to provide a variety of food options to ensure crew members' psychological well-being. 4.4.3 Psychological support. The isolation and confinement of space travel, combined with the long duration of the mission, can have a significant impact on the mental well-being of astronauts. To address this, psychological support systems will be in place to help crew members cope with the challenges they may face. Regular communication with mission control and their families back on Earth will be encouraged to maintain a sense of connection and support. Additionally, astronauts will undergo extensive psychological training before the mission to develop coping mechanisms and resilience. 4.4.4 Medical care and monitoring. A comprehensive medical care system will be established on board the spacecraft to address any potential health issues that may arise during the mission. The crew will have access to medical supplies, diagnostic equipment, and telemedicine capabilities to communicate with medical professionals on Earth. Regular health checkups and monitoring of vital signs will be conducted to detect any early signs of illness or physiological changes. Astronauts will also receive training in basic medical procedures to address minor medical issues themselves. 4.4.5 Sleep and circadian rhythm management. Maintaining a healthy sleep pattern is crucial for the well-being and performance of the crew. In the microgravity environment of the spacecraft, astronauts may experience disturbances in their sleep patterns and circadian rhythms. To mitigate this, the spacecraft will be equipped with individual sleeping quarters designed to provide a comfortable and conducive environment for sleep. Lighting systems will be implemented to simulate natural day-night cycles, helping astronauts maintain their circadian rhythms. 4.4.6 Radiation protection. One of the significant challenges of a Mars mission is the exposure to radiation during the journey. The crew will be exposed to higher levels of radiation compared to Earth due to the absence of a protective atmosphere. To minimize the risks, the spacecraft will be equipped with shielding materials to reduce radiation exposure. Additionally, crew members will be required to wear radiation protection garments during critical periods of high radiation, such as during solar flares. 4.4.7 Team dynamics and conflict resolution. Living and working in close quarters for an extended period can lead to interpersonal conflicts and strained relationships among the crew. To maintain a harmonious and productive environment, crew members will undergo extensive training in team dynamics and conflict resolution techniques. Effective communication, active listening, and empathy will be emphasized to foster a positive and supportive team atmosphere. Mission Control will also provide guidance and support in resolving any conflicts that may arise. 4.4.8 Emergency Medical Procedures. Despite all the precautions taken to ensure crew health, emergencies can still occur during the mission. Crew members will receive training in emergency medical procedures to handle critical situations. This includes basic life support techniques, first aid, and the use of medical equipment and supplies. Mission Control will also provide remote guidance and support in case of medical emergencies that require advanced medical intervention. In conclusion, maintaining the health and well-being of the crew during a mission to Mars is of utmost importance. Through a combination of physical fitness, proper nutrition, psychological support, medical care, sleep management, radiation protection, team dynamics, and emergency preparedness, astronauts will be equipped to face the challenges of the journey and carry out their mission successfully. The lessons learned from these efforts will not only benefit future Mars missions but also contribute to our understanding of human health and well-being in extreme environments. 5. Arrival and landing. 5.1 Entry, Descent, and Landing Systems. The successful landing of a spacecraft on Mars is a critical and complex task that requires careful planning and precise execution. Entry, Descent, and Landing (EDL) systems play a crucial role in ensuring a safe touchdown on the Martian surface. This section will explore the various components and technologies involved in the EDL process. 5.1.1 Atmospheric Entry. The journey to Mars begins with the spacecraft entering the Martian atmosphere. As the spacecraft approaches Mars, it must withstand the intense heat generated by atmospheric friction. To protect the spacecraft from the extreme temperatures, a heat shield is used. The heat shield is made of materials that can withstand temperatures of up to several thousand degrees Celsius. During atmospheric entry, the spacecraft experiences tremendous deceleration due to the drag caused by the Martian atmosphere. This deceleration is managed by the use of parachutes, which are deployed to slow down the spacecraft. The parachutes provide additional drag, reducing the spacecraft's velocity and allowing for a controlled descent. 5.1.2 Descent and Landing. After the initial deceleration, the spacecraft enters the descent phase. At this stage, the parachutes are no longer sufficient to slow down the spacecraft to a safe landing speed. To further reduce the velocity, additional systems such as retro-rockets or airbags are employed. Retro-rockets are engines that are fired to counteract the downward motion of the spacecraft and reduce its speed. These engines provide thrust in the opposite direction, allowing for a controlled descent. The retro-rockets are carefully timed and controlled to ensure a precise landing. In some missions, airbags are used as an alternative to retro-rockets. These airbags are deployed just before touchdown and act as cushions, absorbing the impact of the landing. The spacecraft bounces on the surface, gradually losing momentum until it comes to a stop. Once the spacecraft has settled, the airbags deflate, and the spacecraft begins its surface operations. 5.1.3 Guidance and Navigation. Accurate guidance and navigation systems are crucial for a successful landing on Mars. These systems rely on a combination of sensors, cameras, and onboard computers to determine the spacecraft's position, velocity, and orientation during descent. One of the key technologies used in guidance and navigation is the radar. Radar systems on board the spacecraft emit radio waves towards the Martian surface and measure the time it takes for the waves to bounce back. By analyzing the reflected signals, the radar can determine the distance to the surface and provide valuable information for the landing sequence. In addition to radar, cameras are also used to capture images of the Martian surface during descent. These images help the onboard computers to identify potential hazards such as large rocks or steep slopes. The computers can then adjust the landing trajectory to avoid these obstacles and ensure a safe touchdown. 5.1.4 Challenges and Innovations. The process of landing on Mars poses several challenges due to the planet's thin atmosphere, variable weather conditions, and rough terrain. The thin atmosphere makes it difficult to slow down the spacecraft, requiring the use of advanced technologies such as supersonic retropropulsion. Supersonic retropropulsion involves firing engines in the opposite direction of travel to slow down the spacecraft. This technique allows for a more controlled descent and reduces the reliance on parachutes or airbags. It has been successfully used in recent Mars missions, such as the Mars Science Laboratory (MSL) mission that delivered the Curiosity rover to the Martian surface. Another challenge is the unpredictable Martian weather, including dust storms and high winds. These weather conditions can affect the descent and landing process, making it necessary to have robust systems that can adapt to changing conditions. Advanced algorithms and real-time data analysis are used to make adjustments during descent and ensure a safe landing. Innovations in landing systems continue to be a focus of research and development. Concepts such as precision landing, where the spacecraft can target specific landing sites with high accuracy, are being explored. This would enable missions to land in scientifically interesting areas or near potential resources. Conclusion. The entry, descent, and landing systems are critical components of a Mars mission. They enable spacecraft to safely navigate the Martian atmosphere, decelerate, and touch down on the surface. The development of advanced technologies and innovative landing systems has significantly improved the success rate of Mars landings. As we continue to explore Mars, further advancements in EDL systems will be crucial in enabling more ambitious missions and expanding our understanding of the Red Planet. 5.2 Choosing landing sites on Mars. Choosing the right landing site on Mars is a critical decision that can greatly impact the success of a mission. The selection process involves careful consideration of various factors, including scientific objectives, safety, accessibility, and resource availability. In this section, we will explore the key considerations and challenges involved in choosing landing sites on Mars. 5.2.1 Scientific Objectives. One of the primary considerations when selecting a landing site on Mars is the scientific objectives of the mission. Different regions of Mars offer unique opportunities for scientific exploration and discovery. Scientists and mission planners aim to select landing sites that have the potential to provide valuable insights into the planet's geology, climate, history, and potential for past or present life. For example, areas with evidence of ancient riverbeds or deltas may indicate the presence of water in the past, making them attractive targets for studying Mars' geological and hydrological history. Similarly, regions with exposed rock layers or impact craters can provide valuable information about the planet's geological processes and history. 5.2.2 Safety and Accessibility. Safety is a crucial factor when choosing a landing site on Mars. Mission planners must consider the terrain, topography, and atmospheric conditions to ensure a safe landing and subsequent surface operations. Landing sites with relatively flat terrain and low elevation are generally preferred to minimize the risk of landing mishaps. Accessibility is another important consideration. The landing site should be easily reachable from the intended trajectory of the spacecraft. Factors such as the planet's rotation, atmospheric conditions, and the availability of suitable landing sites along the trajectory play a significant role in determining the accessibility of a potential landing site. 5.2.3 Resource Availability. Future human missions to Mars will require access to essential resources such as water, oxygen, and building materials. Therefore, selecting landing sites with potential resource availability is crucial for long-term sustainability and self-sufficiency on the planet. Scientists and mission planners look for signs of water ice, which can be used for drinking, agriculture, and the production of rocket propellant. Additionally, the presence of minerals and elements that can be extracted and utilized for construction and manufacturing purposes is also considered. 5.2.4 Environmental Conditions. The environmental conditions at a potential landing site are critical for the safety and well-being of the astronauts. Factors such as temperature, radiation levels, and dust storms need to be carefully evaluated. Extreme temperature variations on Mars, with average temperatures ranging from -80°C to 20°C, pose challenges for human missions. Landing sites that offer moderate temperatures and protection from extreme weather conditions are preferred. Radiation is another significant concern. Mars lacks a protective magnetic field, exposing the surface to higher levels of radiation compared to Earth. Selecting landing sites with lower radiation levels or natural shielding, such as underground caves or lava tubes, can help mitigate this risk. Dust storms on Mars can be intense and long-lasting, posing a threat to surface operations and equipment. Mission planners consider the frequency and severity of dust storms when selecting landing sites to minimize the impact on mission activities. 5.2.5 Previous missions and data. Previous missions to Mars have provided valuable data and insights into the planet's surface conditions, geology, and potential landing sites. Mission planners analyze the data collected by orbiters, rovers, and landers to identify regions of interest and potential landing sites. The Mars Reconnaissance Orbiter, for example, has provided high-resolution images and detailed maps of the Martian surface, aiding in the identification of potential landing sites. Rovers like Curiosity and Perseverance have explored specific regions, providing valuable information about the geological composition and habitability of different areas. Mission planners leverage this wealth of data to narrow down potential landing sites and make informed decisions based on the available information. 5.2.6 Balancing Factors. Choosing a landing site on Mars involves striking a balance between various factors. Mission planners must consider the scientific objectives, safety, accessibility, resource availability, environmental conditions, and previous mission data to make an informed decision. Trade-offs are often necessary, as certain landing sites may excel in one aspect but fall short in others. For example, a landing site with high scientific potential may have challenging terrain or extreme environmental conditions. Mission planners must carefully evaluate the risks and benefits associated with each potential landing site to ensure the overall success of the mission. In conclusion, choosing a landing site on Mars is a complex and multifaceted process. It requires careful consideration of scientific objectives, safety, accessibility, resource availability, environmental conditions, and previous mission data. By carefully evaluating these factors, mission planners can select landing sites that maximize scientific discovery while ensuring the safety and success of future missions to the Red Planet. 5.3 Mars Surface Operations. Once the Mars spacecraft successfully lands on the surface of the Red Planet, the real work of exploration and colonization begins. Mars surface operations are crucial for the success of any mission to Mars, as they involve a wide range of activities aimed at studying the Martian environment, establishing a human presence, and conducting scientific research. In this section, we will explore the various aspects of Mars surface operations and the challenges that astronauts will face while living and working on Mars. 5.3.1 Establishing a base camp. The first task upon landing on Mars is to establish a base camp that will serve as the central hub for all activities. This base camp will provide a safe and habitable environment for the astronauts, as well as the necessary infrastructure and resources to support their mission. The construction of the base camp will involve deploying inflatable habitats, setting up power generation systems, and establishing communication and life support systems. 5.3.2 EVA Extravehicular Activity. Once the base camp is established, astronauts will begin conducting extravehicular activities (EVAs) to explore the Martian surface. EVAs will involve astronauts venturing outside the habitat in specially designed spacesuits to collect samples, conduct experiments, and perform maintenance tasks. These EVAs will be carefully planned and executed, taking into consideration the harsh Martian environment, including the thin atmosphere, extreme temperatures, and potential dust storms. 5.3.3 Scientific Research. One of the primary objectives of Mars surface operations is to conduct scientific research to better understand the Martian environment and its potential for supporting life. Astronauts will be equipped with a range of scientific instruments and tools to study the geology, climate, and atmosphere of Mars. They will collect samples of rocks, soil, and ice, which will be analyzed in on-site laboratories to search for signs of past or present life and to gain insights into the planet's history. 5.3.4 Resource Utilization. Another important aspect of Mars surface operations is the utilization of local resources to support human presence on the planet. Mars is rich in resources such as water ice, which can be extracted and purified for drinking water, agriculture, and fuel production. Astronauts will also explore the possibility of mining Martian regolith for building materials and extracting valuable minerals. The successful utilization of Martian resources will be crucial for long-term sustainability and self-sufficiency on Mars. 5.3.5 Agriculture and Food Production. To sustain a human presence on Mars, astronauts will need to establish a reliable food production system. This will involve growing crops in controlled environments, such as greenhouses, using hydroponics or other innovative farming techniques. The cultivation of plants will not only provide a source of fresh food but also contribute to the recycling of waste and the production of oxygen through photosynthesis. 5.3.6 Maintenance and Repairs. Living and working on Mars will require regular maintenance and repairs of equipment and infrastructure. Astronauts will need to be trained in various technical skills to troubleshoot and fix any issues that may arise. This will include repairing life support systems, maintaining power generation systems, and ensuring the functionality of communication and navigation systems. The ability to perform these tasks efficiently and effectively will be crucial for the success of Mars surface operations. 5.3.7 Psychological and Physical Health. Living in a confined and isolated environment on Mars for an extended period can have significant psychological and physical effects on astronauts. Mars surface operations will include regular monitoring of the astronauts' health and well-being, both physically and mentally. Exercise routines, recreational activities, and social interactions will be essential to maintain the astronauts' mental health and prevent feelings of isolation and boredom. Additionally, medical support and telemedicine capabilities will be in place to address any health issues that may arise during the mission. 5.3.8 Communication and Collaboration. Effective communication and collaboration will be vital for the success of Mars surface operations. Astronauts will need to maintain constant communication with mission control on Earth to receive instructions, report their findings, and seek guidance when needed. They will also collaborate with scientists and researchers from around the world to analyze data, share findings, and contribute to the global scientific community. Advanced communication systems will be in place to ensure reliable and efficient communication between Mars and Earth. 5.3.9 Safety and Emergency Preparedness. Living and working on Mars comes with inherent risks and challenges. Mars surface operations will prioritize safety and emergency preparedness to mitigate these risks. Astronauts will undergo extensive training in emergency procedures and protocols, including evacuation plans, fire safety, medical emergencies, and contingency plans for natural disasters or equipment failures. Regular drills and simulations will be conducted to ensure that the crew is well prepared to handle any unforeseen situations. In conclusion, Mars surface operations are a critical phase of any mission to Mars. They involve establishing a base camp, conducting EVAs, performing scientific research, utilizing local resources, maintaining infrastructure, ensuring the well-being of astronauts, and maintaining effective communication with Earth. The success of Mars surface operations will pave the way for long-term human presence and exploration on the Red Planet. 5.4 Deploying Habitat and Infrastructure. Deploying a habitat and infrastructure on Mars is a crucial step in establishing a sustainable human presence on the planet. In order to support long-duration missions and ensure the well-being of astronauts, it is essential to create a safe and habitable environment that can withstand the harsh conditions of Mars. This section will explore the challenges and strategies involved in deploying habitats and infrastructure on the Martian surface. 5.4.1 Habitat Design and Construction. Designing a habitat for Mars requires careful consideration of various factors, including radiation protection, thermal regulation, and structural integrity. The habitat must provide a comfortable living space for the crew, shielding them from the harmful radiation and extreme temperatures of the Martian environment. One approach to habitat construction is to use inflatable structures. These lightweight and flexible habitats can be transported in a compact form and then inflated on the Martian surface. Inflatable habitats offer several advantages, including ease of transportation, expandability, and radiation protection. They can be made from durable materials that can withstand the harsh conditions of Mars, such as reinforced fabrics or composite materials. Another approach is to use modular habitats that can be assembled on site. These habitats consist of prefabricated modules that can be transported to Mars and connected together to create a larger living space. Modular habitats offer flexibility in terms of size and configuration, allowing for easy expansion or reconfiguration as needed. They can also be designed to provide radiation shielding and thermal insulation. In addition to the main habitat, infrastructure such as power generation, life support systems, and communication networks are essential for sustaining human presence on Mars. Power can be generated through a combination of solar panels and nuclear power systems, providing a reliable source of energy for the habitat and other equipment. Life support systems, including air purification, water recycling, and waste management, are crucial for maintaining a sustainable living environment. Communication networks, both with Earth and between different habitats or exploration sites on Mars, enable efficient coordination and data exchange. 5.4.2 Construction Techniques and Materials. Constructing habitats and infrastructure on Mars poses unique challenges due to the limited availability of resources and the harsh environmental conditions. In order to minimize the need for transporting materials from Earth, it is important to utilize local resources and employ innovative construction techniques. One approach is to use in situ resource utilization (ISRU) to extract and process Martian resources for construction purposes. For example, regolith, the loose soil and rocks covering the Martian surface, can be used as a building material. By processing regolith and binding it with a suitable binder, it can be transformed into a durable construction material. This approach not only reduces the need for transporting construction materials from Earth but also enables the construction of structures that are specifically tailored to the Martian environment. Another technique is 3D printing, which allows for the construction of complex structures using local resources. By using a robotic arm or a mobile printer, structures can be built layer by layer using a variety of materials, including regolith or other locally available resources. 3D printing offers advantages such as reduced construction time, flexibility in design, and the ability to create intricate structures that are difficult to achieve with traditional construction methods. To ensure the durability and longevity of the habitat and infrastructure, it is important to consider the effects of the Martian environment. The thin atmosphere and low atmospheric pressure on Mars can lead to increased wear and tear on structures. Therefore, materials and construction techniques must be carefully selected to withstand the harsh conditions, including temperature fluctuations, dust storms, and radiation exposure. 5.4.3 Maintenance and Upgrades. Once the habitat and infrastructure are deployed on Mars, regular maintenance and upgrades are necessary to ensure their continued functionality and adaptability to changing needs. Maintenance tasks may include repairing damaged structures, replacing worn-out components, and conducting routine inspections to identify potential issues. In order to minimize the need for human intervention, autonomous systems and robotics can be employed for maintenance and repairs. Robotic systems can be designed to perform tasks such as structural inspections, repairs, and equipment replacements. These systems can be remotely operated from Earth or controlled by astronauts on Mars, depending on the complexity of the task. Upgrades to the habitat and infrastructure may be required to accommodate new technologies, improve efficiency, or expand the capabilities of the mission. For example, advancements in life support systems or energy generation technologies may necessitate the installation of new equipment or the modification of existing systems. Upgrades can also be made to enhance the comfort and well-being of the crew, such as improving living quarters or recreational facilities. 5.4.4 Environmental Considerations. Deploying habitat and infrastructure on Mars must be done in a way that minimizes the environmental impact on the planet. Planetary protection protocols, which aim to prevent contamination of Mars with Earth organisms and vice versa, must be strictly followed during the construction and operation of the habitat. Special care must be taken to ensure that no biological or organic material is introduced to Mars, as it could interfere with the search for potential life or contaminate the Martian environment. Furthermore, the construction and operation of the habitat should be designed to minimize energy consumption and waste generation. Sustainable practices, such as recycling and efficient resource utilization, should be implemented to reduce the environmental footprint of the mission. This includes minimizing water usage, managing waste effectively, and implementing energy-efficient systems. In conclusion, deploying a habitat and infrastructure on Mars is a complex and challenging task that requires careful planning, innovative construction techniques, and consideration of environmental impact. By designing habitats that provide radiation protection, thermal regulation, and structural integrity, and by utilizing local resources and employing advanced construction techniques, we can create a sustainable and habitable environment for astronauts on Mars. Regular maintenance, upgrades, and adherence to planetary protection protocols are essential for the long-term success of the mission. 6. Exploring the Martian environment. 6.1 Geology and geographical features of Mars. Mars, often referred to as the Red Planet, has captivated the imagination of scientists and space enthusiasts for centuries. One of the key aspects of Mars that has intrigued researchers is its geology and geographical features. Understanding the geological history and the unique characteristics of the Martian landscape is crucial for any mission to the planet. 6.1.1 Martian surface. The surface of Mars is vastly different from that of Earth. Mars is home to the largest volcano in the solar system, Olympus Mons, which stands at a staggering height of 13.6 miles, 22 kilometers, and has a diameter of about 370 miles, 600 kilometers. This shield volcano is a prominent feature on the Martian surface and is a testament to the planet's volcanic past. In addition to Olympus Mons, Mars is also home to other notable volcanoes such as Arsia Mons, Pavonis Mons, and Ascraeus Mons. These volcanoes, although not as large as Olympus Mons, still showcase the planet's volcanic activity. Apart from volcanoes, Mars is also known for its vast plains and canyons. The Valles Marineris, a system of canyons that stretches for about 2,500 miles, 4,000 kilometers, across the Martian surface, is one of the most striking features of the planet. This canyon system is about 6 miles, 10 kilometers, deep and as a result of tectonic activity and erosion over millions of years. 6.1.2 Impact craters. Like Earth, Mars has been bombarded by asteroids and comets throughout its history. These impacts have left behind numerous craters on the Martian surface. Some of these craters are well preserved, providing valuable insights into the planet's geological past. One of the most famous impact craters on Mars is the Hellas Planitia, located in the southern hemisphere. This impact basin is about 1,200 miles, 2,000 kilometers, in diameter and is one of the largest impact craters in the solar system. The presence of such large impact craters suggests that Mars experienced a period of intense bombardment early in its history. Studying these impact craters can provide scientists with information about the age of the Martian surface and the geological processes that have shaped it over time. By analyzing the composition of the rocks and sediments within these craters, scientists can gain insights into the planet's past climate and the presence of water. 6.1.3 Polar ice caps. One of the most intriguing features of Mars is its polar ice caps. Similar to Earth's polar ice caps, Mars has both a North Polar ice cap and a South Polar ice cap. These ice caps are composed mainly of water ice, but they also contain a significant amount of frozen carbon dioxide, also known as dry ice. The polar ice caps on Mars undergo seasonal changes, with the ice expanding and contracting depending on the planet's tilt and its distance from the Sun. During the Martian winter, a significant portion of the atmosphere condenses and freezes onto the polar ice caps, causing them to grow in size. As the Martian summer approaches, the ice caps begin to melt, releasing gases back into the atmosphere. The study of these polar ice caps is crucial for understanding the planet's climate history and the potential availability of water resources for future human missions. The presence of water ice on Mars opens up possibilities for sustaining life and supporting future colonization efforts. 6.1.4 Martian dust storms. Mars is known for its frequent and sometimes massive dust storms. These storms can cover the entire planet and last for weeks or even months. Martian dust storms are driven by strong winds that can reach speeds of up to 60 miles per hour, 100 kilometers per hour. These dust storms have a significant impact on the Martian surface and atmosphere. They can alter the temperature and atmospheric pressure, affect the planet's climate, and even contribute to the erosion of surface features. The dust storms also play a role in the planet's water cycle, as they can lift dust particles into the atmosphere, which can then act as condensation nuclei for the formation of clouds. Studying these dust storms is crucial for understanding the Martian climate and its potential impact on future human missions. The ability to predict and mitigate the effects of dust storms will be essential for the safety and success of any mission to Mars. In conclusion, Mars is a planet with a rich geological history and unique geographical features. From its towering volcanoes to its vast canyons and impact craters, Mars offers a wealth of opportunities for scientific exploration and discovery. Understanding the geology and geography of Mars is crucial for planning and executing successful missions to the planet, as well as for unraveling the mysteries of its past and potential for supporting life. 6.2 Searching for water and resources. One of the primary objectives of exploring Mars is to search for water and resources that could potentially support human life and future colonization efforts. Water is a crucial resource for sustaining life as we know it, and its presence on Mars could significantly impact the feasibility of long-term human missions to the planet. In addition to water, the search for other resources such as minerals and elements necessary for fuel production and construction materials is also of great importance. 6.2.1 The importance of water on Mars. Water is essential for human survival, and its presence on Mars would be a game changer for future missions. Not only can water be used for drinking and food production, but it can also be broken down into its constituent elements, hydrogen and oxygen, to produce breathable air and rocket propellant. Therefore, finding accessible sources of water on Mars is crucial for sustaining human presence on the planet. Scientists have discovered evidence of water on Mars in various forms. The presence of polar ice caps, composed mainly of water ice, has been known for a long time. Additionally, recent missions have provided strong evidence of liquid water in the form of briny flows on the Martian surface. These findings suggest that water may exist in liquid form beneath the surface, potentially in underground aquifers or trapped within minerals. 6.2.2 Techniques for detecting water. To search for water on Mars, scientists and engineers have developed a range of techniques and instruments. These instruments are designed to analyze the Martian surface, subsurface, and atmosphere for signs of water and its related compounds. One of the most effective methods for detecting water on Mars is through the use of remote sensing instruments. These instruments, such as spectrometers and radar systems, can analyze the composition and properties of the Martian surface from orbit. By measuring the reflection and absorption of specific wavelengths of light, scientists can identify the presence of water ice and other hydrated minerals. In addition to remote sensing, rovers and landers equipped with drilling and sampling capabilities have been deployed to directly analyze the Martian soil and rocks. These missions, such as the Mars rovers Curiosity and Perseverance, have successfully detected and analyzed water-bearing minerals and provided valuable insights into the history and distribution of water on Mars. 6.2.3 Mapping water resources. To effectively utilize water resources on Mars, it is crucial to map their distribution and accessibility. Scientists and engineers use a combination of remote sensing data, geological mapping, and in situ measurements to identify potential water-rich regions on the planet. One approach is to study the geological features known as recurring slope linei, RSL. These dark streaks on Martian slopes are believed to be caused by the seasonal flow of briny water. By mapping the distribution and characteristics of RSL, scientists can identify regions where liquid water may be present near the surface. Another method is to analyze the composition of Martian meteorites that have fallen to Earth. These meteorites provide valuable information about the geological history and water content of Mars. By studying their isotopic composition and mineralogy, scientists can gain insights into the distribution and abundance of water on the planet. 6.2.4 Extracting and utilizing Martian water. Once water resources are identified, the next challenge is to develop technologies for extracting and utilizing them. Various methods have been proposed for extracting water from the Martian environment, including drilling, heating, and chemical processes. One approach is to use drilling techniques to access subsurface water reservoirs. By drilling deep into the Martian soil, scientists can potentially tap into underground aquifers or ice deposits. Once accessed, the water can be extracted and purified for various uses, such as drinking, irrigation, and fuel production. Another method is to utilize the abundant carbon dioxide, CO2, in the Martian atmosphere. CO2 can be converted into oxygen and carbon monoxide through a process called in situ resource utilization, ISRU. The oxygen produced can be used for breathing, while the carbon monoxide can be combined with hydrogen, extracted from water, to produce methane, a potential rocket propellant. 6.2.5 Resource prospecting and mining. In addition to water, Mars is also rich in various resources that could be valuable for future human missions. These resources include minerals, metals, and elements necessary for fuel production, construction, and life support systems. Prospecting for resources on Mars involves the identification and characterization of potential resource-rich regions. This can be done through remote sensing techniques, geological mapping, and in situ measurements. By analyzing the composition and distribution of minerals and elements, scientists can identify regions with high resource potential. Mining on Mars would involve the extraction and processing of resources for various purposes. This could include the extraction of metals for construction, the production of fuel from Martian resources, and the utilization of minerals for manufacturing processes. Developing efficient and sustainable mining technologies will be crucial for future Mars missions. In conclusion, the search for water and resources on Mars is of paramount importance for future human missions and colonization efforts. Water, in particular, is a vital resource that could support human life and enable the production of essential supplies such as breathable air and rocket propellant. By utilizing a combination of remote sensing, in situ measurements, and resource prospecting techniques, scientists and engineers are working towards unlocking the potential of Mars as a sustainable and habitable planet for future generations of explorers. 6.3 Studying Martian atmosphere and climate. The study of the Martian atmosphere and climate is a crucial aspect of exploring the Red Planet. Understanding the atmospheric conditions and climate patterns on Mars is essential for various reasons, including planning future missions, assessing the potential for sustaining life, and gaining insights into the planet's geological history. 6.3.1 Composition of the Martian atmosphere. The Martian atmosphere is significantly different from Earth's atmosphere. It is composed mainly of carbon dioxide, CO2, with trace amounts of nitrogen, argon, and oxygen. The thin atmosphere on Mars is approximately 100 times less dense than Earth's atmosphere, making it challenging for humans to survive without proper life support systems. Studying the composition of the Martian atmosphere provides valuable information about the planet's evolution and its potential habitability. Scientists analyze the presence of different gases and their variations over time to understand the processes that have shaped the Martian atmosphere. 6.3.2 Climate patterns on Mars. Mars experiences a wide range of climate patterns, including dust storms, temperature variations, and seasonal changes. These climate patterns have a significant impact on the planet's surface and its potential for supporting life. Dust storms are a common occurrence on Mars and can vary in size and intensity. These storms can last for weeks or even months, covering large areas of the planet with dust and reducing visibility. Studying these dust storms helps scientists understand the atmospheric dynamics and the role they play in shaping the Martian climate. Temperature variations on Mars are extreme, with average temperatures ranging from -80 degrees Fahrenheit, -62 degrees Celsius, to -195 degrees Fahrenheit, -125 degrees Celsius. These temperature fluctuations are primarily due to the thin atmosphere, which cannot retain heat effectively. Understanding the temperature patterns on Mars is crucial for designing habitats and spacesuits that can withstand the harsh conditions. Mars also experiences seasonal changes, similar to Earth. The planet's axial tilt and elliptical orbit around the Sun result in variations in sunlight and temperature throughout the year. These seasonal changes affect the distribution of water ice, the behavior of the atmosphere, and the potential for liquid water on the surface. 6.3.3 Atmospheric Dynamics and Weather. Studying the atmospheric dynamics and weather on Mars provides insights into the planet's climate system and its potential for sustaining life. Mars has a thin atmosphere, which means that weather phenomena such as clouds, wind, and precipitation are significantly different from those on Earth. Clouds on Mars are primarily composed of water ice crystals or carbon dioxide ice particles. These clouds can form at different altitudes and play a role in the planet's weather patterns. Studying the formation and behavior of clouds helps scientists understand the water cycle on Mars and its impact on the overall climate. Wind patterns on Mars are influenced by various factors, including the planet's topography, temperature gradients, and atmospheric circulation. Dust storms, mentioned earlier, are often driven by strong winds that can transport dust particles across the planet. Understanding the wind patterns on Mars is crucial for predicting the movement of dust storms and their potential impact on future missions. Precipitation on Mars is rare, but it does occur in the form of snow or frost. Water ice can accumulate on the surface during certain seasons, especially in the polar regions. Studying the occurrence and distribution of precipitation helps scientists assess the availability of water resources on Mars and its potential for supporting future human settlements. 6.3.4 Climate change on Mars. Just like Earth, Mars has undergone significant climate changes throughout its history. Studying these changes provides valuable insights into the planet's geological evolution and its potential for sustaining life. One of the most significant climate changes on Mars is the transition from a warmer and wetter environment to the cold and arid conditions we observe today. Evidence suggests that Mars once had a denser atmosphere and liquid water on its surface, which raises intriguing questions about the possibility of past life on the planet. Understanding the factors that led to the climate change on Mars, such as the loss of its magnetic field and the thinning of its atmosphere, is crucial for unraveling the planet's history. By studying the geological features and analyzing the composition of rocks and sediments, scientists can reconstruct the past climate conditions on Mars and gain insights into its potential habitability. Conclusion. Studying the Martian atmosphere and climate is a fundamental aspect of exploring the Red Planet. By analyzing the composition of the atmosphere, studying climate patterns, and investigating weather phenomena, scientists can gain a deeper understanding of Mars' past, present, and future. This knowledge is essential for planning future missions, assessing the potential for sustaining life, and unraveling the mysteries of our neighboring planet. 6.4 Investigating potential for past or present life. The search for life beyond Earth has always been a fundamental question in the field of space exploration. Mars, with its similarities to Earth and the possibility of hosting life, has been a prime target for scientists and researchers. In this section, we will delve into the various methods and technologies used to investigate the potential for past or present life on Mars. 6.4.1 Martian microbial life. One of the primary objectives of exploring Mars is to search for evidence of microbial life. Microbes are known to thrive in extreme environments on Earth, and Mars, with its harsh conditions, presents a similar environment where life could potentially exist. Scientists have discovered extremophiles on Earth that can survive in extreme temperatures, high radiation levels, and low nutrient environments, providing hope that similar life forms could exist on Mars. To investigate the potential for microbial life on Mars, scientists have developed a range of instruments and techniques. One such instrument is the Mars Organic Analyzer (MOA), which is designed to detect organic compounds, the building blocks of life, in Martian soil samples. By analyzing the chemical composition of the soil, scientists can determine if the conditions on Mars are conducive to supporting life. Another important tool in the search for microbial life is the Mars Sample Return Mission. This ambitious mission aims to collect samples from the Martian surface and bring them back to Earth for detailed analysis. By studying these samples in laboratories on Earth, scientists can conduct more comprehensive investigations into the presence of microbial life on Mars. 6.4.2 Signs of ancient life. In addition to searching for present-day microbial life, scientists are also interested in uncovering evidence of ancient life on Mars. The planet's geological history suggests that it may have once had a more hospitable environment, with liquid water and a thicker atmosphere. These conditions could have provided a suitable habitat for more complex forms of life to evolve. One approach to investigating signs of ancient life is through the study of Martian rocks and minerals. By analyzing the composition and structure of these materials, scientists can look for patterns and signatures that indicate the presence of past life. For example, certain minerals, such as hematite and jarosite, are known to form in the presence of water, suggesting that liquid water may have once existed on Mars. Another method of searching for signs of ancient life is through the exploration of Martian caves and underground habitats. These subsurface environments could have provided protection from harsh surface conditions and may have preserved evidence of past life. Robotic missions equipped with drilling and sampling capabilities could be used to access these underground regions and collect samples for analysis. 6.4.3 Biosignatures and biomarkers. To identify signs of past or present life on Mars, scientists rely on the detection of biosignatures and biomarkers. Biosignatures are indirect indicators of life, such as the presence of certain chemicals or the alteration of the environment by living organisms. Biomarkers, on the other hand, are specific molecules or compounds that are produced by living organisms and can serve as direct evidence of life. One example of a potential biomarker on Mars is methane. On Earth, methane is produced by both biological and geological processes. The detection of methane in the Martian atmosphere could indicate the presence of microbial life, as it is known to be produced by certain types of bacteria. The Curiosity rover has detected intermittent methane levels on Mars, sparking excitement among scientists and further fueling the search for life. In addition to methane, scientists are also interested in the detection of other organic compounds, such as amino acids and nucleotides, which are the building blocks of proteins and DNA, respectively. These organic compounds are essential for life as we know it, and their presence on Mars would provide strong evidence for the existence of past or present life. 6.4.4 Challenges and future prospects. Investigating the potential for past or present life on Mars is a complex and challenging task. The harsh Martian environment, with its thin atmosphere, extreme temperatures, and high radiation levels, poses significant challenges for the survival of any potential life forms. Additionally, the search for life requires sophisticated instruments and technologies that can accurately detect and analyze the presence of biosignatures and biomarkers. Despite these challenges, the exploration of Mars continues to provide valuable insights into the potential for life beyond Earth. As technology advances and our understanding of Mars improves, future missions will be equipped with more advanced instruments and capabilities, allowing for more detailed investigations into the possibility of life on the Red Planet. In conclusion, investigating the potential for past or present life on Mars is a crucial aspect of Mars exploration. By searching for microbial life, signs of ancient life, and detecting biosignatures and biomarkers, scientists are working towards unraveling the mysteries of Mars and understanding the potential for life beyond our home planet. The ongoing exploration of Mars brings us closer to answering the age-old question, are we alone in the universe? 7. Living on Mars. 7.1 Habitat Design and Construction. As humans embark on the ambitious mission to explore and eventually settle on Mars, one of the most critical aspects to consider is the design and construction of habitats that can sustain human life in the harsh Martian environment. The success of a Mars mission heavily relies on the ability to create safe and habitable spaces for astronauts to live and work in. This chapter delves into the intricacies of habitat design and construction, exploring the challenges faced and the innovative solutions developed to overcome them. 7.1.1 Environmental Considerations. Designing a habitat on Mars requires a deep understanding of the planet's unique environmental conditions. Mars has a thin atmosphere, extreme temperatures, high radiation levels, and a lack of breathable air. These factors pose significant challenges that must be addressed in the design process. To protect astronauts from the harsh radiation on Mars, habitats need to be shielded with thick layers of radiation-resistant materials. This can include using regolith, Martian soil, as a shielding material or incorporating advanced radiation-blocking technologies. Additionally, the habitats must be well insulated to regulate temperature and protect against extreme cold and heat. Innovative insulation materials and heating systems are being developed to ensure the comfort and safety of the crew. 7.1.2 Habitat Architecture. The architecture of a Martian habitat plays a crucial role in providing a functional and comfortable living space for astronauts. The design must optimize the use of available resources while ensuring structural integrity and ease of construction. One approach to habitat design is the use of inflatable structures. These lightweight and compact modules can be transported to Mars in a compressed form and then inflated upon arrival. Inflatable habitats offer several advantages, including reduced launch mass, ease of transportation, and the ability to expand the living space as needed. They can also provide radiation protection and insulation when properly designed. Another approach is the use of modular habitats. These habitats consist of prefabricated modules that can be assembled on site. The modules can be designed to serve specific functions, such as living quarters, laboratories, and storage areas. This modular approach allows for flexibility in design and easy expansion of the habitat as the mission progresses. 7.1.3 Construction Techniques. Constructing habitats on Mars presents unique challenges due to the limited availability of resources and the need for self-sufficiency. Traditional construction methods used on Earth, such as pouring concrete or using heavy machinery, are not feasible on Mars. Therefore, innovative construction techniques are being developed to overcome these limitations. One promising technique is 3D printing. By utilizing Martian regolith as a building material, 3D printers can create structures layer by layer, eliminating the need for transporting bulky construction materials from Earth. This approach not only reduces the launch mass but also allows for the construction of complex and customized designs. Researchers are actively exploring the use of 3D printing to build habitats, infrastructure, and even tools and equipment on Mars. Another approach is the use of in situ resource utilization, ISRU. This involves extracting and utilizing resources available on Mars, such as water ice and carbon dioxide, to produce construction materials. For example, water ice can be melted and used as a binding agent for regolith, creating a type of Martian concrete. ISRU not only reduces the reliance on Earth for resources but also enables the construction of habitats and infrastructure using locally available materials. 7.1.4 Life Support Systems. In addition to providing a safe and comfortable living space, habitats on Mars must also incorporate life support systems to sustain the crew. These systems are responsible for providing breathable air, clean water, and managing waste. To ensure a continuous supply of breathable air, habitats will rely on advanced air filtration and recycling systems. These systems will remove carbon dioxide exhaled by the crew and convert it back into oxygen through processes like electrolysis. Water management systems will be crucial for recycling and purifying water, as well as extracting water from Martian resources. Waste management systems will be designed to efficiently process and dispose of solid and liquid waste generated by the crew. 7.1.5 Psychological Considerations. Living on Mars for an extended period can have significant psychological impacts on astronauts. The isolation, confinement, and distance from Earth can lead to feelings of loneliness and homesickness. Therefore, habitat design must also address the psychological well-being of the crew. Creating habitats with ample space, natural lighting, and views of the Martian landscape can help alleviate feelings of confinement. Incorporating recreational areas, exercise facilities, and personal spaces can provide astronauts with opportunities for relaxation and personal time. Additionally, communication systems that enable regular contact with loved ones on Earth can help mitigate feelings of isolation. In conclusion, the design and construction of habitats on Mars is a complex and multifaceted task. It requires careful consideration of environmental conditions, innovative architectural designs, advanced construction techniques, and robust life support systems. By addressing these challenges, scientists and engineers are paving the way for a future where humans can not only survive but thrive on the red planet. 7.2 Food production and agriculture. 7.2.1 The challenge of feeding astronauts on Mars. One of the most critical challenges of long-duration space missions, such as a mission to Mars, is ensuring a sustainable and reliable food supply for the astronauts. Unlike on Earth, where we have abundant natural resources and a supportive environment for agriculture, Mars presents a harsh and inhospitable environment for growing crops. The lack of a breathable atmosphere, extreme temperatures, and high levels of radiation make it impossible to cultivate traditional crops outdoors. To overcome this challenge, scientists and engineers have been exploring innovative solutions for food production and agriculture in space. The goal is to develop sustainable systems that can provide astronauts with a nutritious and balanced diet throughout their mission, reducing the need for resupply missions from Earth. 7.2.2 Controlled environment agriculture. One approach to food production on Mars is through controlled environment agriculture, CEA. CE involves creating enclosed environments, such as greenhouses or growth chambers, where plants can be cultivated under controlled conditions. These environments provide the necessary protection from the harsh Martian environment and allow for the optimization of temperature, humidity, light, and nutrient levels. In a Martian greenhouse, plants can be grown hydroponically or aeroponically, without the need for soil. Hydroponics involves growing plants in nutrient-rich water solutions, while aeroponics involves growing plants in a mist or air environment with nutrient-rich sprays. Both methods have been successfully used on Earth and have the potential to be adapted for Martian conditions. 7.2.3 Plant selection and adaptation. Selecting the right plants for Martian agriculture is crucial. Scientists are studying various plant species to determine their adaptability to the Martian environment. Factors such as nutrient requirements, growth rate, water usage, and tolerance to radiation and low atmospheric pressure are taken into consideration. Certain crops, such as leafy greens, herbs, and some root vegetables, have shown promise for Martian agriculture. These crops have relatively short growth cycles and can provide essential vitamins and minerals to the astronauts. Additionally, some plants, like algae, can be used for both food and oxygen production through photosynthesis. 7.2.4 Nutrient management and recycling. In a closed system like a Martian greenhouse, nutrient management and recycling are crucial for sustainability. Astronauts will need to carefully monitor and manage the nutrient levels in the water solutions to ensure optimal plant growth. Nutrient solutions can be supplemented with fertilizers derived from waste products, such as human waste or plant residues, which are processed and converted into usable nutrients. Water is a precious resource on Mars, and efficient water management is essential. Techniques such as water purification and recycling will be employed to minimize water consumption. Additionally, technologies for extracting water from Martian soil or from the atmosphere may be developed to supplement the water supply. 7.2.5 Supplementing the diet. While plant-based agriculture will be the primary source of food for astronauts on Mars, it may not be sufficient to meet all their nutritional needs. To ensure a well-balanced diet, other sources of nutrients may be required. This could include incorporating insects, microorganisms, or lab-grown meat into the astronauts' diet. These alternative protein sources can be produced using minimal resources and can provide essential nutrients that may be lacking in plant-based diets. 7.2.6 Psychological and social aspects of food. Food plays a significant role in our psychological well-being and social interactions. On a long-duration mission to Mars, where astronauts will be isolated from Earth and their loved ones, the importance of food as a morale booster cannot be underestimated. Efforts will be made to provide astronauts with a variety of food options, including comfort foods and treats, to help maintain their mental well-being. Additionally, communal dining areas and shared meal times can foster a sense of community and provide opportunities for social interaction among the crew members. The psychological and social aspects of food should not be overlooked when designing food production and consumption systems for Mars missions. 7.2.7 Future prospects and innovations. As we continue to explore the challenges of food production and agriculture on Mars, new technologies and innovations will undoubtedly emerge. Advances in genetic engineering, plant breeding, and automation can revolutionize the way we grow food in space. Scientists are also exploring the potential of using Martian regolith soil as a growth medium, which could reduce the need for importing soil from Earth. Furthermore, the knowledge and experience gained from Mars missions can have significant implications for sustainable agriculture on Earth. The technologies and techniques developed for space farming could be applied to improve food production in arid regions or areas affected by climate change, helping to address global food security challenges. In conclusion, food production and agriculture are critical components of sustaining human life on Mars. Through controlled environment agriculture, careful plant selection, nutrient management, and innovative approaches, we can overcome the challenges of growing food in the harsh Martian environment. The success of these efforts will not only ensure the well-being of astronauts on Mars but also pave the way for future space exploration and contribute to advancements in sustainable agriculture on Earth. 7.3 Water and waste management. Water and waste management are crucial aspects of living on Mars. As humans venture to the Red Planet, ensuring a sustainable and efficient system for water usage and waste disposal becomes paramount. In this section, we will explore the challenges of managing water resources on Mars and discuss innovative solutions for waste management in the Martian environment. 7.3.1 Water resources on Mars. Water is essential for human survival, and finding accessible sources of water on Mars is a top priority for future missions. Although Mars is known to have water in the form of ice at its poles and in underground reservoirs, extracting and utilizing this water poses significant challenges. One approach to obtaining water on Mars is through in situ resource utilization, ISRU. ISRU involves extracting and processing resources available on Mars to sustain human missions. Scientists and engineers are developing techniques to extract water from Martian ice and convert it into usable forms, such as liquid water or hydrogen and oxygen for fuel production. Another potential source of water on Mars is the atmosphere. Mars has a thin atmosphere that contains trace amounts of water vapor. Scientists are exploring methods to extract and condense this water vapor for human consumption and other uses. These techniques could provide a sustainable source of water for future Martian settlements. 7.3.2 Water conservation and recycling. Given the limited availability of water on Mars, conservation and recycling are essential practices. Water conservation measures, such as efficient water usage and minimizing wastage, will be crucial to ensure the long-term sustainability of Martian habitats. To maximize water efficiency, technologies like advanced filtration systems and water purification techniques will be employed. These systems will remove impurities and contaminants from water sources, making them safe for consumption and other uses. Additionally, water recycling systems will be implemented to treat and reuse wastewater, reducing the need for constant resupply from Earth. 7.3.3 Waste management on Mars. Proper waste management is vital for maintaining a clean and healthy living environment on Mars. Waste generated by human activities, including food waste, packaging materials, and other byproducts, must be managed effectively to prevent contamination and ensure the sustainability of Martian habitats. One approach to waste management on Mars is recycling. Recycling systems will be implemented to process and reuse materials whenever possible. This will reduce the need for constant resupply from Earth and minimize the accumulation of waste. In addition to recycling, other waste management techniques will be employed. Composting organic waste can be a valuable method for producing nutrient-rich soil for agriculture on Mars. Waste materials that cannot be recycled or composted may need to be safely stored or disposed of in designated areas to prevent environmental contamination. 7.3.4 Human waste management. Managing human waste is a critical aspect of maintaining hygiene and preventing the spread of diseases on Mars. Advanced toilet systems will be developed to efficiently collect and process human waste, ensuring the safety and well-being of the crew. One potential solution is the use of closed-loop systems that separate solid and liquid waste. Solid waste can be processed and converted into fertilizer or used for other purposes, while liquid waste can be treated and recycled for various applications, such as irrigation or water reclamation. To minimize the risk of contamination, strict protocols and procedures will be established for handling and disposing of human waste. These protocols will ensure that waste is properly contained and treated to prevent any potential harm to the Martian environment and the health of the crew. 7.3.5 Future Challenges and Innovations. While significant progress has been made in understanding water and waste management on Mars, many challenges remain. The harsh Martian environment, including extreme temperatures and low atmospheric pressure, presents unique obstacles to overcome. Future missions will require continued research and development to improve water extraction techniques, enhance water conservation methods, and optimize waste management systems. Innovations in technology and engineering will play a crucial role in addressing these challenges and ensuring the long-term sustainability of human presence on Mars. In conclusion, water and waste management are critical considerations for living on Mars. The limited availability of water resources necessitates efficient usage, conservation, and recycling. Waste management systems must be implemented to minimize environmental contamination and maintain a healthy living environment. As we continue to explore and colonize Mars, advancements in technology and innovative solutions will be essential to overcome the challenges of water and waste management in the Martian environment. 7.4 Healthcare and Medical Support. 7.4.1 Health Challenges on Mars. As humans embark on the mission to Mars, one of the most critical aspects to consider is healthcare and medical support. The journey to Mars and the prolonged stay on the planet pose numerous challenges to the physical and mental well-being of astronauts. The harsh Martian environment, including reduced gravity, radiation exposure, and isolation, can have significant impacts on the health of the crew. 7.4.1.1 Microgravity Effects. During the journey to Mars, astronauts will experience microgravity conditions, which can lead to various physiological changes in the human body. Prolonged exposure to microgravity can result in muscle and bone loss, cardiovascular deconditioning, and alterations in the immune system. To mitigate these effects, astronauts will undergo rigorous exercise routines and receive nutritional support to maintain their physical health. 7.4.1.2 Radiation exposure. Another major concern for astronauts on Mars is radiation exposure. Unlike Earth, Mars lacks a protective magnetic field, leaving its surface exposed to high levels of cosmic radiation. This radiation can increase the risk of cancer, damage DNA, and impair the functioning of vital organs. Shielding measures and advanced radiation monitoring systems will be crucial to minimize the astronauts' exposure to radiation during their stay on Mars. 7.4.1.3 Psychological and social factors. Living in a confined and isolated environment for an extended period can have significant psychological and social impacts on astronauts. The psychological well-being of the crew will be closely monitored, and support systems, including regular communication with loved ones on Earth and access to mental health professionals, will be in place to address any psychological challenges that may arise. 7.4.2 Medical Support Systems. To ensure the health and safety of astronauts on Mars, robust medical support systems will be an integral part of the mission. These systems will include advanced diagnostic tools, medical supplies, and equipment necessary for emergency medical procedures. Additionally, the crew will receive extensive medical training to handle minor medical issues and emergencies that may arise during their stay on Mars. 7.4.2.1 Telemedicine and Remote Medical Assistance. Given the distance between Mars and Earth, it will be essential to establish effective telemedicine capabilities. Through real-time communication and video conferencing, medical professionals on Earth will be able to provide remote medical assistance to the crew on Mars. This will enable the diagnosis and treatment of medical conditions that may require specialized expertise not available on the spacecraft. 7.4.2.2 Surgical Capabilities. In the event of a medical emergency that requires surgical intervention, the crew will have access to a fully equipped medical facility on the spacecraft. This facility will be equipped with surgical instruments, sterilization equipment, and anesthesia capabilities. The crew will receive specialized training in surgical procedures to address any life-threatening situations that may arise during their mission. 7.4.2.3 Medication and Pharmaceutical Supplies. A comprehensive inventory of medications and pharmaceutical supplies will be available on the spacecraft to address various medical conditions that may occur during the mission. These supplies will include antibiotics, pain relievers, anti-nausea medications, and other essential drugs. Additionally, research will be conducted to develop new medications and treatments specifically tailored to the unique challenges of living on Mars. 7.4.3 Crew Health Monitoring. Continuous monitoring of the crew's health will be crucial to detect and address any medical issues promptly. Advanced medical monitoring devices will be used to track vital signs, blood chemistry, and other physiological parameters. This data will be transmitted to medical professionals on Earth for analysis and consultation. Regular health checkups and screenings will be conducted to ensure the crew's well-being throughout their stay on Mars. 7.4.4 Emergency Medical Evacuation. Despite all the precautions and medical support systems in place, there may be situations where emergency medical evacuation becomes necessary. In such cases, a dedicated emergency return vehicle will be available to transport the affected crew member back to Earth for advanced medical care. The spacecraft will be equipped with the necessary life support systems and medical equipment to ensure the safe return of the crew member. 7.4.5 Psychological support. Living on Mars for an extended period can be mentally challenging for astronauts. To address the psychological well-being of the crew, psychological support systems will be in place. This will include regular counseling sessions, access to virtual reality environments for relaxation and stress reduction, and recreational activities to promote social interaction and combat feelings of isolation. 7.4.6 Research and Development. The mission to Mars will provide a unique opportunity to conduct research and development in the field of healthcare and medical support. The data collected during the mission will contribute to a better understanding of the physiological and psychological effects of long-duration space travel. This knowledge will not only benefit future Mars missions but also have implications for healthcare on Earth, leading to advancements in medical technology and treatments. In conclusion, healthcare and medical support will be of paramount importance for the success of a mission to Mars. The challenges posed by the Martian environment, including microgravity, radiation exposure, and psychological factors, necessitate robust medical support systems, telemedicine capabilities, and comprehensive crew health monitoring. By addressing these challenges and continuously advancing medical technology, we can ensure the well-being and safety of astronauts on their journey to Mars. 8. Working on Mars. 8.1 Exploration and Field Research. Exploration and field research are crucial components of any mission to Mars. Once astronauts have landed on the Martian surface, they must embark on a series of scientific investigations and experiments to gather data and expand our understanding of the Red Planet. This chapter will delve into the various aspects of exploration and field research on Mars, including the goals, methods, and challenges faced by astronauts. 8.1.1 Goals of Exploration. The primary goal of exploration on Mars is to unravel the mysteries of the planet and gain insights into its geological history, potential for life, and habitability. By studying the Martian environment up close, scientists hope to answer fundamental questions about the planet's past, present, and future. Some of the key objectives of exploration and field research on Mars include: geological studies. Mars is a treasure trove of geological wonders, with its vast canyons, towering volcanoes, and ancient impact craters. Astronauts will conduct detailed geological surveys to understand the planet's formation, tectonic activity, and erosion processes. By analyzing rock samples and studying the composition of Martian soil, scientists can piece together the planet's geological history. Search for water. Water is a crucial ingredient for life as we know it. Exploring Mars involves searching for evidence of past or present water on the planet. Astronauts will investigate the presence of water ice in the polar regions, study the behavior of liquid water, and analyze the composition of Martian soil to determine the planet's water resources. Atmospheric and climate studies. Understanding the Martian atmosphere and climate is essential for future human missions and potential colonization. Astronauts will collect data on atmospheric composition, temperature, pressure, and weather patterns. This information will help scientists model the planet's climate and predict future changes. Life detection. One of the most intriguing questions about Mars is whether life exists or has ever existed on the planet. Astronauts will conduct experiments to search for signs of microbial life, such as analyzing soil samples for organic compounds and studying the potential for subsurface habitats. The discovery of even simple forms of life on Mars would have profound implications for our understanding of the origin and prevalence of life in the universe. 8.1.2 Methods of Exploration. Exploration and field research on Mars involve a combination of scientific experiments, sample collection, and data analysis. Astronauts will utilize advanced equipment and technologies to carry out their investigations. Some of the key methods of exploration on Mars include: rover missions. Robotic rovers have been instrumental in exploring the Martian surface. These vehicles are equipped with a variety of scientific instruments, cameras, and drills to collect samples and gather data. Astronauts will continue to utilize rovers to extend their reach and explore regions that are difficult to access on foot. Sample collection. Collecting rock and soil samples is a crucial part of field research on Mars. Astronauts will use specialized tools and equipment to collect samples from different geological formations. These samples will be carefully stored and eventually returned to Earth for detailed analysis in laboratories. Geological mapping. Astronauts will create detailed geological maps of the Martian surface to identify key features and potential areas of scientific interest. This mapping will help scientists understand the planet's geology and guide future exploration efforts. Remote sensing. Remote sensing techniques, such as using orbiting satellites and landers, will play a vital role in exploration and field research on Mars. These methods allow scientists to gather data on the planet's surface, atmosphere, and climate from a distance. Astronauts will work in collaboration with these remote sensing technologies to enhance their understanding of the Martian environment. 8.1.3 Challenges and Considerations. Exploration and field research on Mars present numerous challenges and considerations that astronauts must overcome. Some of the key challenges include: harsh environment. Mars is an inhospitable environment with extreme temperatures, low atmospheric pressure, and high levels of radiation. Astronauts must be equipped with advanced spacesuits and protective gear to survive and work in these conditions. Limited resources. Unlike Earth, Mars does not have readily available resources such as air, water, and food. Astronauts must rely on efficient resource management and recycling systems to sustain themselves during their mission. Communication delay. Due to the vast distance between Earth and Mars, there is a significant delay in communication. Astronauts must be prepared to work autonomously and make critical decisions without real-time guidance from mission control. Isolation and psychological factors. Mars missions involve long-duration stays on the planet, which can lead to feelings of isolation and psychological stress. Astronauts must undergo rigorous training and psychological support to cope with the challenges of living and working in a confined and isolated environment. Despite these challenges, exploration and field research on Mars offer immense opportunities for scientific discovery and the advancement of human knowledge. The data and insights gathered from these missions will pave the way for future human exploration and potential colonization of the Red Planet. 8.2 Resource utilization and mining. As humans embark on the mission to Mars, one of the key challenges they face is the need for self-sufficiency. In order to establish a sustainable presence on the Red Planet, astronauts must learn to utilize the resources available to them on Mars itself. Resource utilization and mining will play a crucial role in ensuring the success of long-duration missions and the eventual colonization of Mars. 8.2.1 In situ resource utilization, ISRU. In situ resource utilization, or ISRU, refers to the practice of utilizing resources found on Mars rather than relying solely on supplies brought from Earth. This approach is essential for reducing the cost and complexity of missions, as well as ensuring the availability of vital resources for the crew. The resources that can be potentially utilized on Mars include water, carbon dioxide, and regolith, the loose, rocky material covering the planet's surface. Water extraction and purification. Water is a critical resource for human survival, and it is also a valuable resource for various other purposes, such as fuel production and agriculture. Mars is known to have significant amounts of water ice in its polar regions and possibly underground. Extracting and purifying this water will be a top priority for astronauts on Mars. Various techniques, such as drilling, melting, and filtering, can be employed to extract and purify water from ice deposits or subsurface sources. Carbon dioxide utilization. The Martian atmosphere is composed mostly of carbon dioxide, CO2, which can be converted into oxygen, O2, for breathing and is a propellant for rockets. Carbon dioxide can be extracted from the atmosphere and processed through a series of chemical reactions to produce oxygen. This process, known as in situ resource utilization, will be crucial for sustaining the crew and enabling future missions to Mars. Regolith mining. Regolith, the loose soil and rocks covering the Martian surface, contains various minerals and elements that can be utilized for construction, manufacturing, and energy production. Mining regolith will involve the use of robotic systems and advanced excavation techniques to extract valuable resources such as iron, aluminum, silicon, and titanium. These resources can be used to build habitats, infrastructure, and even produce fuel for return missions. 8.2.2 Challenges and opportunities. Resource utilization and mining on Mars present several challenges and opportunities for astronauts and future colonists. Some of the key challenges include: harsh Martian environment. The Martian environment is harsh and unforgiving, with extreme temperatures, low atmospheric pressure, and high levels of radiation. These conditions pose significant challenges for resource utilization and mining operations. Astronauts will need to develop robust and reliable technologies that can withstand the harsh environment and operate autonomously for extended periods. Limited resources. While Mars does offer resources such as water and regolith, they are limited in quantity and distribution. Astronauts will need to carefully manage and conserve these resources to ensure their long-term availability. Recycling and reusing materials will be essential to minimize waste and maximize resource utilization. Technological development. Resource utilization and mining on Mars will require the development of advanced technologies and innovative solutions. From autonomous mining robots to efficient extraction and processing systems, significant technological advancements will be necessary to make resource utilization on Mars a reality. Collaboration between space agencies, research institutions, and private companies will be crucial in driving these technological developments. Despite the challenges, resource utilization and mining on Mars also present numerous opportunities. By learning to live off the land, humans can reduce their dependence on Earth and establish a self-sustaining presence on another planet. The knowledge and technologies developed for resource utilization on Mars can also have significant applications on Earth, such as in sustainable mining practices and resource management. 8.2.3 Environmental considerations. While resource utilization and mining on Mars offer great potential, it is essential to consider the environmental impact of these activities. As humans explore and exploit the resources of another planet, it is crucial to do so in a responsible and sustainable manner. Some key considerations include: planetary protection. Planetary protection aims to prevent contamination of Mars with Earth organisms and vice versa. Strict protocols and procedures will need to be in place to ensure that resource utilization and mining activities do not inadvertently introduce harmful microorganisms to Mars or contaminate Earth with potentially hazardous Martian materials. Preservation of Martian ecosystems. Although Mars is currently believed to be devoid of life, future missions may uncover evidence of past or present microbial life. It is important to preserve any potential Martian ecosystems and conduct thorough scientific investigations before engaging in resource utilization and mining activities that could disrupt or destroy these ecosystems. Minimizing environmental footprint. Resource utilization and mining operations should strive to minimize their environmental footprint on Mars. This includes minimizing waste generation, implementing efficient recycling systems, and adopting sustainable practices. By minimizing the impact on the Martian environment, humans can ensure the long-term viability of their presence on the planet. In conclusion, resource utilization and mining will be crucial for the success of missions to Mars and the eventual colonization of the Red Planet. By harnessing the resources available on Mars, such as water, carbon dioxide, and regolith, astronauts can establish a self-sustaining presence and reduce their reliance on Earth. However, it is important to approach resource utilization and mining in a responsible and sustainable manner, considering the environmental impact and preserving the potential for scientific discoveries on Mars. 8.3 Scientific experiments and observations. Scientific experiments and observations play a crucial role in any mission to Mars. The primary objective of these experiments is to gather data and information about the Martian environment, its geology, atmosphere, climate, and the potential for life. By conducting these experiments, scientists hope to gain a deeper understanding of Mars and its history, as well as to pave the way for future exploration and potential colonization. 8.3.1 Studying the Martian atmosphere. One of the key scientific experiments conducted on Mars is the study of its atmosphere. The Martian atmosphere is significantly different from Earth's, consisting mainly of carbon dioxide with traces of nitrogen and argon. By analyzing the composition and behavior of the Martian atmosphere, scientists can gain insights into the planet's climate, weather patterns, and potential for sustaining life. One important aspect of studying the Martian atmosphere is understanding its dynamics and how it interacts with the planet's surface. Scientists use various instruments and sensors to measure temperature, pressure, humidity, and wind patterns. These measurements help in creating models and simulations to better understand the atmospheric processes on Mars. Another crucial aspect of studying the Martian atmosphere is investigating the presence of methane. Methane is a gas that can be produced by both biological and geological processes. Its detection on Mars has sparked great interest as it could be an indicator of potential microbial life. Scientists use spectrometers and other instruments to analyze the concentration and distribution of methane in the Martian atmosphere, providing valuable insights into the planet's habitability. 8.3.2 Analyzing Martian soil and rocks. The geology of Mars is a fascinating subject of study, and scientists have conducted numerous experiments to analyze the composition and structure of Martian soil and rocks. By examining the minerals and elements present in the Martian regolith, scientists can gain insights into the planet's geological history, including volcanic activity, impact cratering, and the presence of water. One of the most significant scientific experiments conducted on Mars is the analysis of soil and rock samples using rovers and landers. These missions, such as the Mars Science Laboratory (MSL) with the Curiosity rover, have provided valuable data about the Martian surface. Instruments like X-ray diffraction and spectrometers help identify the minerals present in the samples, providing clues about the past and present conditions on Mars. In addition to analyzing the composition of Martian soil and rocks, scientists also study their physical properties. By measuring properties like density, porosity, and magnetic susceptibility, scientists can gain insights into the formation processes and history of the Martian surface. These experiments help in understanding the potential for past or present habitability and the availability of resources for future human missions. 8.3.3 Searching for signs of water. Water is a crucial resource for future human missions to Mars, and scientists are actively searching for signs of its presence on the planet. The search for water involves studying the Martian surface, subsurface, and the atmosphere. One of the key experiments conducted to search for water on Mars is the analysis of hydrated minerals. These minerals, which contain water molecules within their crystal structure, can provide evidence of past or present water activity. Rovers and landers equipped with spectrometers and cameras have been used to identify and analyze these minerals, helping scientists map the distribution of water-related minerals on Mars. Another important experiment is the study of Martian polar ice caps. These ice caps consist of a mixture of water ice and carbon dioxide ice. By analyzing the composition and structure of the ice caps, scientists can gain insights into the history of Martian climate and the potential availability of water resources for future missions. Scientists also study the Martian atmosphere to understand the water cycle on the planet. By measuring humidity, temperature, and cloud formation, scientists can gain insights into the presence and behavior of water vapor in the Martian atmosphere. These experiments help in understanding the potential for atmospheric water resources and the possibility of using them for future human missions. 8.3.4 Investigating potential for life. One of the most exciting aspects of Mars exploration is the search for signs of past or present life. Scientists conduct various experiments and observations to investigate the potential for life on Mars. One important experiment is the search for organic molecules. Organic molecules are the building blocks of life as we know it, and their detection on Mars could indicate the presence of past or present life. Rovers and landers equipped with instruments like gas chromatographs and mass spectrometers have been used to analyze Martian soil and rock samples for organic molecules. While the detection of organic molecules does not necessarily prove the existence of life, it provides valuable clues and motivates further exploration. Scientists also study the potential for microbial life in extreme environments on Earth, known as extremophiles. By understanding the limits of life on Earth, scientists can better assess the potential for life in extreme environments on Mars. Experiments involving the cultivation of extremophiles in simulated Martian conditions help in understanding the survival strategies of microorganisms and their potential for colonization on Mars. In addition to direct experiments, scientists also use remote sensing techniques to search for signs of life on Mars. Instruments like spectrometers and cameras on orbiters and rovers help in identifying features like methane plumes, seasonal changes, and potential biosignatures. These observations provide valuable data for further investigation and guide the selection of future landing sites for more detailed exploration. Scientific experiments and observations on Mars are essential for expanding our knowledge of the planet and its potential for sustaining life. The data and insights gained from these experiments pave the way for future missions and colonization efforts, as well as contribute to our understanding of the universe and our place in it. 8.4 Technology Development and Innovation. Technology development and innovation play a crucial role in the success of any mission to Mars. As humans venture further into space, the need for advanced technologies becomes even more apparent. In this section, we will explore the various technological advancements and innovations that are essential for a successful mission to Mars. 8.4.1 Advanced Propulsion Systems. One of the key areas of technology development for Mars missions is advanced propulsion systems. Traditional chemical propulsion systems, such as those used in rockets, have limitations in terms of efficiency and speed. To overcome these limitations, scientists and engineers are exploring alternative propulsion technologies. One such technology is ion propulsion, which uses electrically charged particles to generate thrust. Ion propulsion systems are highly efficient and can provide continuous thrust over long durations. These systems are being developed and tested for interplanetary travel, including missions to Mars. Another promising technology is nuclear propulsion, which utilizes the energy released from nuclear reactions to generate thrust. Nuclear propulsion systems have the potential to significantly reduce travel time to Mars, making it a more feasible option for human exploration. However, the development and implementation of nuclear propulsion systems require extensive research and careful consideration of safety measures. 8.4.2 In situ resource utilization (ISRU). In situ resource utilization (ISRU) is a critical aspect of technology development for Mars missions. ISRU involves utilizing resources available on Mars, such as water, minerals, and gases, to support human exploration and settlement. This approach reduces the need to transport all necessary supplies from Earth, making missions more sustainable and cost-effective. One of the primary resources of interest on Mars is water. Water can be used for various purposes, including drinking, growing plants, and producing rocket propellant. Scientists are developing technologies to extract water from Martian ice caps or subsurface deposits and purify it for human consumption and other uses. ISRU also involves the extraction and utilization of Martian minerals and gases. These resources can be used for construction, manufacturing, and energy production. Technologies for mining and processing Martian resources are being developed, including robotic systems capable of autonomously extracting and processing materials. 8.4.3 Advanced Life Support Systems. For long-duration missions to Mars, advanced life support systems are crucial to ensure the health and well-being of astronauts. These systems provide a controlled environment that mimics Earth's conditions, including temperature, humidity, and air composition. They also manage waste, recycle water, and provide food and oxygen for the crew. Technology development in this area focuses on improving the efficiency and reliability of life support systems. This includes advancements in air revitalization, water recycling, waste management, and food production. Scientists are exploring innovative solutions, such as bioregenerative systems that use plants to recycle air and produce food. Additionally, research is being conducted on the psychological and physiological effects of long-duration space travel. This knowledge helps in the development of technologies and strategies to mitigate the negative impacts of space travel on the human body and mind. 8.4.4 Robotics and Automation. Robotic exploration of Mars has been instrumental in gathering data and conducting experiments before human missions. As technology continues to advance, robots are becoming more capable and autonomous, enabling them to perform complex tasks on the Martian surface. Technology development in robotics focuses on improving mobility, dexterity, and autonomy. Robotic systems are being designed to traverse challenging terrains, collect samples, and perform scientific experiments. These robots can be remotely operated from Earth or operate autonomously using artificial intelligence algorithms. Automation is also a key aspect of technology development for Mars missions. Automated systems can perform routine tasks, freeing up human astronauts to focus on more critical activities. Automation can also enhance efficiency and reduce the risk of human error in various mission operations, such as maintenance, resource utilization, and data analysis. 8.4.5 Communication and Data Management. Effective communication and data management are essential for successful Mars missions. The vast distances between Earth and Mars introduce significant communication delays, making real-time communication impossible. Therefore, technology development in this area focuses on developing robust communication systems that can handle the long delays and ensure reliable data transmission. Advanced communication systems, such as deep space networks and relay satellites, are being developed to establish continuous communication links with Mars. These systems enable the transmission of large amounts of data, including scientific observations, images, and video feeds. Data management is another critical aspect of technology development. Mars missions generate vast amounts of data that need to be stored, processed, and analyzed. Scientists are developing efficient data storage and processing techniques, including artificial intelligence algorithms, to handle the massive volumes of data collected during missions. 8.4.6 Innovative Materials and Structures. Innovative materials and structures are essential for the construction of habitats, spacecraft, and infrastructure on Mars. Traditional materials used on Earth may not be suitable for the harsh Martian environment, which is characterized by extreme temperatures, radiation, and low atmospheric pressure. Scientists and engineers are developing new materials that can withstand the Martian conditions while being lightweight and durable. These materials include advanced composites, ceramics, and alloys. Additionally, 3D printing technology is being explored as a means to construct habitats and infrastructure using locally available resources. Innovative structural designs are also being developed to ensure the safety and stability of Martian structures. These designs consider factors such as Martian gravity, seismic activity, and the need for radiation shielding. By utilizing advanced materials and innovative structural designs, future Mars missions can establish sustainable habitats and infrastructure. Conclusion. Technology development and innovation are crucial for the success of missions to Mars. Advancements in propulsion systems, in situ resource utilization, life support systems, robotics, communication, data management, and materials are paving the way for human exploration and settlement on the Red Planet. These technologies not only enable us to reach Mars but also ensure the safety, sustainability, and efficiency of future missions. With continued research and development, we are inching closer to the day when humans will set foot on Mars and embark on a new era of interplanetary exploration. 9. Return from Mars. 9.1 Preparation for return journey. As the time comes for the astronauts to leave the Martian surface and embark on their journey back to Earth, careful preparation and planning are crucial. The return journey from Mars is a complex and challenging endeavor that requires meticulous attention to detail and the implementation of various strategies to ensure a safe and successful return. 9.1.1 Evaluating mission objectives. Before initiating the return journey, the mission team must evaluate whether all the primary objectives of the mission have been achieved. This assessment involves reviewing the data collected, analyzing the results of experiments and observations, and determining if any additional tasks need to be completed before departure. It is essential to make the most of the time spent on Mars and gather as much valuable information as possible to contribute to scientific knowledge and future missions. 9.1.2 Assessing resources and supplies. Another critical aspect of preparing for the return journey is assessing the available resources and supplies. The mission team must evaluate the remaining food, water, and oxygen reserves to ensure that there is enough to sustain the crew during the journey back to Earth. If necessary, contingency plans should be in place to address any shortages or unexpected circumstances that may arise. 9.1.3 Maintenance and repairs. Before leaving Mars, it is essential to conduct a thorough inspection of the spacecraft and its systems to identify any potential issues or damages that may have occurred during the mission. Any necessary repairs or maintenance tasks should be carried out to ensure that the spacecraft is in optimal condition for the return journey. This includes checking the life support systems, propulsion systems, communication and navigation systems, and any other critical components. 9.1.4 Preparing the spacecraft for departure. Preparing the spacecraft for departure involves a series of meticulous procedures to ensure a smooth transition from the Martian surface to the interplanetary trajectory. This includes retracting any deployed structures, securing loose equipment, and stowing away any samples or scientific instruments that were used during the mission. The crew must also ensure that the habitat and infrastructure are properly secured for the journey. 9.1.5 Calculating the optimal launch window. Timing is crucial when it comes to the return journey from Mars. The mission team must calculate the optimal launch window, which is the period when the alignment of Earth and Mars allows for the most efficient transfer orbit. This involves considering various factors such as the positions of the planets, fuel requirements, and the desired trajectory. The launch window is typically a narrow timeframe, and missing it could result in significant delays or even the need to wait for the next favorable opportunity. 9.1.6 Trajectory planning and course corrections. Once the launch window is determined, trajectory planning becomes a critical task. The mission team must calculate the most efficient trajectory to return to Earth, taking into account factors such as fuel consumption, gravitational assists, and potential course corrections along the way. Continuous monitoring of the spacecraft's trajectory is necessary to ensure that it remains on the intended path and to make any necessary adjustments to maintain the desired course. 9.1.7 Radiation protection. During the return journey, the crew will be exposed to increased levels of radiation due to the absence of the protective magnetic field of Earth. Therefore, it is crucial to implement effective radiation protection measures to minimize the health risks for the astronauts. This may include shielding the crew compartment with materials that can absorb or deflect radiation, as well as monitoring radiation levels and providing appropriate medical support. 9.1.8 Crew Health and Well-being. Maintaining the health and well-being of the crew during the return journey is of utmost importance. The mission team must ensure that the astronauts have access to adequate medical supplies, including medications and equipment, to address any potential health issues that may arise. Regular health checkups and monitoring should be conducted to detect and address any medical concerns promptly. 9.1.9 Communication and Navigation. Throughout the return journey, maintaining reliable communication and navigation systems is crucial for the crew's safety and for keeping mission control informed of the spacecraft's status. The mission team must ensure that the communication systems are functioning correctly and that there are backup systems in place in case of any failures. Navigation systems should be continuously monitored and calibrated to ensure accurate positioning and trajectory calculations. 9.1.10 Psychological preparation. Returning from Mars after an extended period of time can be emotionally challenging for the crew. The mission team must provide psychological support and prepare the astronauts for the transition back to Earth's gravity, atmosphere, and social environment. This may involve counseling sessions, debriefings, and activities to help the crew readjust and cope with the physical and psychological changes they may experience. In conclusion, the preparation for the return journey from Mars is a critical phase of the mission. It involves evaluating mission objectives, assessing resources, conducting maintenance and repairs, preparing the spacecraft for departure, calculating the optimal launch window, planning the trajectory, implementing radiation protection measures, ensuring crew health and well-being, maintaining communication and navigation systems, and providing psychological preparation. By carefully addressing these aspects, the mission team can ensure a safe and successful return from Mars, bringing valuable knowledge and experiences back to Earth. 9.2 Launch from Mars and interplanetary transit. Once the mission on Mars has been successfully completed, the next crucial step is the launch from the Martian surface and the interplanetary transit back to Earth. This phase of the mission requires careful planning and execution to ensure the safe return of the astronauts and the valuable scientific data collected during their stay on Mars. 9.2.1 Preparations for departure. Before the launch can take place, several preparations need to be made. The first step is to ensure that the spacecraft is in optimal condition for the journey back to Earth. This includes conducting thorough checks of all systems, including life support, communication, navigation, and propulsion. Any necessary repairs or maintenance must be carried out to guarantee the spacecraft's functionality. Additionally, the crew must undergo a series of medical evaluations to ensure they are fit for the return journey. The extended stay on Mars may have taken a toll on their physical and mental well-being, so it is crucial to address any health concerns before embarking on the long trip back home. 9.2.2 Launch from Mars. Launching a spacecraft from the surface of Mars poses unique challenges compared to launches from Earth. The Martian atmosphere is much thinner, with only about 1% of the density of Earth's atmosphere. This means that traditional rocket propulsion systems, which rely on the expulsion of gases for thrust, are not as effective on Mars. To overcome this challenge, alternative launch methods have been proposed. One possibility is to use a combination of chemical rockets and aerodynamic lift. The spacecraft could be equipped with wings or other aerodynamic surfaces to generate lift, allowing it to gradually ascend through the Martian atmosphere. Once it reaches a certain altitude, the chemical rockets would take over and propel the spacecraft into space. Another option is to utilize a space elevator concept, where a cable or tether is anchored to the Martian surface and extends into space. The spacecraft would then climb the tether using a combination of propulsion and mechanical assistance, similar to how an elevator operates on Earth. This method would significantly reduce the amount of fuel required for launch, making it a more efficient and sustainable option. 9.2.3 Interplanetary transit. After successfully launching from Mars, the spacecraft begins its interplanetary transit back to Earth. This phase of the mission can take several months or even years, depending on the alignment of the planets and the chosen trajectory. During this time, the crew must continue to maintain their physical and mental well-being while also monitoring the spacecraft's systems and conducting scientific experiments. One of the primary challenges during interplanetary transit is the exposure to cosmic radiation. Unlike Earth, Mars does not have a protective magnetic field or a thick atmosphere to shield against harmful radiation from the sun and deep space. Therefore, the spacecraft must be equipped with adequate shielding to minimize the astronauts' exposure to radiation. Additionally, the crew may need to take regular breaks from their duties to rest and recover from the effects of prolonged space travel. Communication with mission control on Earth is also crucial during interplanetary transit. The spacecraft must maintain a reliable and continuous communication link to receive updates, instructions, and support from ground control. Advanced communication and navigation systems are essential to ensure seamless communication and accurate trajectory adjustments if necessary. 9.2.4 Return trajectory and re-entry. As the spacecraft approaches Earth, careful calculations and trajectory adjustments are made to ensure a safe re-entry into the Earth's atmosphere. The timing and angle of re-entry must be precisely calculated to avoid excessive heat and stress on the spacecraft. The goal is to achieve a controlled descent that allows for a safe landing. During re-entry, the spacecraft experiences intense heat due to the friction between the vehicle and the Earth's atmosphere. Special heat shields are used to protect the spacecraft and its occupants from the extreme temperatures. These heat shields are designed to withstand the high temperatures and dissipate the heat, ensuring the crew's safety. Once the spacecraft has successfully re-entered the Earth's atmosphere, parachutes or other landing systems are deployed to slow down the descent and ensure a gentle landing. The landing site is carefully chosen to provide a safe and accessible location for recovery operations. 9.2.5 Post-mission challenges. Returning from Mars is a significant milestone, but it also presents a new set of challenges for the returning astronauts. After spending an extended period in the reduced gravity of Mars, the crew will need to readjust to the Earth's gravity. This process, known as reintegration, can be physically demanding and may require a period of rehabilitation and medical monitoring. Additionally, the crew will undergo debriefings and scientific analysis of the data collected during the mission. The knowledge gained from the mission will contribute to our understanding of Mars and help shape future exploration efforts. The crew's experiences and insights will also be valuable in refining mission planning and improving the design of spacecraft and habitats for future missions. Returning from Mars is a monumental achievement that requires meticulous planning, advanced technology, and the bravery and dedication of the astronauts involved. It marks the successful completion of a mission that pushes the boundaries of human exploration and brings us one step closer to unlocking the mysteries of the Red Planet. 9.3 Re-entry and landing on Earth. After spending a significant amount of time on Mars, the astronauts of the mission Red Planet are finally ready to return home. However, the journey back to Earth is not without its challenges. Re-entry and landing on Earth require careful planning and execution to ensure the safe return of the crew and the valuable scientific data they have collected. 9.3.1 Re-entry into Earth's atmosphere. The first step in returning from Mars is to leave the Martian orbit and set a trajectory towards Earth. Once the spacecraft is on the correct path, it begins its descent into Earth's atmosphere. Re-entry is a critical and dangerous phase of the mission, as the spacecraft must withstand intense heat and extreme forces. During re-entry, the spacecraft experiences tremendous heat due to the friction between the atmosphere and its high-speed entry. The heat shield, which is designed to withstand temperatures of several thousand degrees Celsius, plays a crucial role in protecting the crew and the spacecraft. The heat shield is made of advanced materials, such as carbon composites and ablative materials, which can absorb and dissipate the heat. As the spacecraft descends further into the atmosphere, it experiences increasing atmospheric drag, which slows it down. This deceleration is necessary to reduce the spacecraft's velocity and allow for a safe landing. The crew inside the spacecraft experiences high levels of gravitational forces, similar to those during launch, as the spacecraft decelerates rapidly. 9.3.2 Parachute deployment and controlled descent. To further slow down the spacecraft and stabilize its descent, parachutes are deployed. These parachutes provide additional drag, reducing the velocity of the spacecraft and ensuring a controlled descent. The parachutes are carefully designed and tested to withstand the forces exerted during deployment and descent. The deployment of parachutes is a critical moment during re-entry, as any failure or malfunction could have catastrophic consequences. The spacecraft's systems are equipped with redundancy and backup mechanisms to ensure the successful deployment of parachutes. Multiple parachutes may be used, each serving a specific purpose, such as stabilization or final descent. As the spacecraft approaches the surface, the crew prepares for the final landing sequence. The spacecraft's systems, including its thrusters and landing gear, are activated to ensure a smooth touchdown. The crew closely monitors the descent and makes any necessary adjustments to ensure a safe landing. 9.3.3 Water landing or land landing. Depending on the mission design and available resources, the spacecraft may either land on water or on land. Water landings are often preferred due to their lower impact forces and the ability to use flotation devices to keep the spacecraft afloat until rescue teams arrive. However, land landings offer the advantage of easier access for recovery and post-landing operations. In the case of a water landing, the spacecraft is designed to remain buoyant and stable until rescue teams arrive. The crew is trained in water survival techniques and is equipped with appropriate safety gear, such as life rafts and flotation devices. Once the crew is safely evacuated, recovery teams retrieve the spacecraft and begin the process of securing it for transportation. For land landings, the spacecraft is equipped with landing gear and shock-absorbing systems to cushion the impact. The crew is prepared for the possibility of a rough landing and is trained to handle emergency situations that may arise during touchdown. Recovery teams are stationed near the landing site to assist with the crew's evacuation and the retrieval of the spacecraft. 9.3.4 Post-landing procedures and crew recovery. After the spacecraft has landed safely, the crew undergoes a series of post-landing procedures to ensure their well-being and to begin the process of reintegration into Earth's environment. Medical teams are on standby to assess the crew's health and provide any necessary medical assistance. The crew is carefully monitored for any signs of physical or psychological stress resulting from their time in space and the journey back to Earth. They undergo a period of quarantine to prevent the potential spread of any Martian microorganisms or contaminants that may have been brought back with them. Once the crew is deemed healthy and free from any potential hazards, they are reunited with their families and loved ones. The crew members undergo debriefings and share their experiences and insights with mission control and the scientific community. The valuable data and samples collected during the mission are carefully analyzed and studied, contributing to our understanding of Mars and its potential for life. The successful re-entry and landing of the mission Red Planet spacecraft marked the end of an extraordinary journey. The crew's safe return to Earth is a testament to the meticulous planning, advanced technology, and the bravery and dedication of the astronauts who ventured to Mars and back. Their achievements pave the way for future missions and inspire the next generation of explorers to reach for the stars. 9.4 Reintegration and Post-Mission Challenges. After spending months or even years on Mars, astronauts face a unique set of challenges when they return to Earth. Reintegration into society and readjustment to life on our home planet can be a complex and sometimes difficult process. Additionally, there are several post-mission challenges that astronauts must navigate as they transition back to their normal lives. In this section, we will explore the reintegration process and the various post-mission challenges that astronauts may encounter. 9.4.1 Reintegration into society. Returning from a mission to Mars is a monumental achievement, but it also comes with its own set of psychological and emotional challenges. Astronauts may experience a sense of disconnection or isolation upon their return, as they have been living in a highly controlled and confined environment on Mars. The vastness and freedom of Earth can be overwhelming, and astronauts may struggle to readjust to the fast-paced and complex nature of life on our planet. One of the key aspects of reintegration is reconnecting with family and loved ones. Astronauts may have missed important milestones and events while they were away, and rebuilding those relationships can take time and effort. Open and honest communication is crucial during this period, as astronauts and their loved ones navigate the changes that have occurred during their absence. Another challenge of reintegration is finding a sense of purpose and meaning after such an extraordinary experience. Astronauts may have a difficult time transitioning from the intense focus and mission-oriented mindset of their time on Mars to the more mundane tasks of everyday life. It is important for astronauts to find new goals and passions to pursue, whether it be in their professional careers or personal lives, in order to maintain a sense of fulfillment and purpose. 9.4.2 Physical and Medical Challenges. The physical toll of living on Mars cannot be underestimated. Astronauts may experience muscle atrophy, bone density loss, and cardiovascular deconditioning during their time in microgravity. Upon returning to Earth's gravity, they will need to undergo a rigorous rehabilitation program to regain their strength and physical capabilities. This process can be demanding and may require months of physical therapy and exercise. In addition to the physical challenges, astronauts may also face medical issues related to their time on Mars. Exposure to radiation during the journey and on the Martian surface can have long-term health effects, including an increased risk of cancer. Astronauts will need to undergo thorough medical evaluations and monitoring to ensure their long-term health and well-being. 9.4.3 Psychological and Emotional Support. The psychological and emotional well-being of astronauts is of utmost importance during the reintegration process. The isolation and confinement of living on Mars can have a profound impact on mental health. Astronauts may experience feelings of loneliness, anxiety, and depression as they adjust to the social and sensory stimulation of Earth. Providing adequate psychological support is crucial to help astronauts navigate these challenges. Regular counseling sessions, both individual and group, can provide a safe space for astronauts to process their experiences and emotions. Additionally, maintaining a strong support network of family, friends, and fellow astronauts can be instrumental in helping astronauts through the reintegration process. 9.4.4 Career Transition and Future Opportunities. Returning from a mission to Mars can also bring about career transitions and new opportunities for astronauts. Many astronauts choose to share their experiences and knowledge by becoming educators or public speakers, inspiring the next generation of explorers. Others may pursue careers in research and development, leveraging their unique insights and expertise gained from their time on Mars. However, transitioning back into a traditional career path can be challenging. Astronauts may find it difficult to fit into a conventional work environment after their extraordinary experiences. Employers and organizations can play a crucial role in supporting astronauts during this transition by providing flexible work arrangements, mentorship programs, and opportunities for continued professional development. 9.4.5 Legacy and Impact. The legacy and impact of a Mars mission extend far beyond the individual astronauts involved. These missions represent a significant milestone in human exploration and inspire future generations to push the boundaries of what is possible. Astronauts have the opportunity to become ambassadors for space exploration, using their experiences to advocate for continued investment in space exploration and research. Additionally, the data and knowledge gathered during the mission can have a lasting impact on scientific advancements and technological innovations. Researchers and scientists will continue to analyze the data collected on Mars, furthering our understanding of the planet and its potential for supporting life. The discoveries made during the mission may also pave the way for future missions and expeditions to Mars. In conclusion, the reintegration process and post-mission challenges faced by astronauts returning from Mars are multifaceted and complex. From reconnecting with loved ones to rebuilding their lives on Earth, astronauts must navigate a range of physical, psychological, and career-related challenges. However, with the right support systems in place, astronauts can successfully transition back into society and continue to make significant contributions to the field of space exploration. 10. Future of Mars exploration. 10.1 Mars colonization and settlement. Mars colonization and settlement have long been a topic of fascination and speculation. As humanity continues to explore the possibilities of space travel and the colonization of other planets, Mars has emerged as a prime candidate for future human habitation. In this section, we will delve into the challenges, opportunities, and potential benefits of colonizing and settling on the Red Planet. 10.1.1 The vision of a Martian colony. The idea of establishing a permanent human presence on Mars has captured the imagination of scientists, engineers, and visionaries for decades. The vision of a Martian colony involves creating a self-sustaining community that can support human life, conduct scientific research, and serve as a stepping stone for further exploration of the solar system. 10.1.2 Challenges of Mars colonization. Colonizing Mars presents numerous challenges that must be overcome. The first and most obvious challenge is the distance. Mars is, on average, about 225 million kilometers away from Earth. This means that any mission to Mars would require a long and arduous journey, lasting several months. The physical and psychological effects of extended space travel pose significant challenges for astronauts. Another major challenge is the harsh Martian environment. Mars has a thin atmosphere, extreme temperatures, and high levels of radiation. The lack of a protective magnetic field also exposes the planet to solar winds and cosmic rays. These conditions make it difficult for humans to survive without the proper infrastructure and technology. 10.1.3 Building a Martian habitat. To establish a sustainable colony on Mars, a habitat capable of supporting human life must be constructed. The habitat would need to provide a controlled environment with breathable air, protection from radiation, and a stable temperature. It would also need to be equipped with systems for water and waste management, as well as food production. One possible approach to building a Martian habitat is to use inflatable structures. These structures could be transported to Mars in a compact form and then inflated upon arrival. They would provide a lightweight and flexible solution for creating living and working spaces. Additionally, the use of 3D printing technology could allow for the construction of habitats using local Martian resources, such as regolith Martian soil. 10.1.4 Sustainable resource utilization. One of the key aspects of Mars colonization is the utilization of local resources to sustain the colony. Mars has abundant resources that can be utilized for various purposes. For example, water ice can be found in the polar regions of Mars, and it can be extracted and purified for drinking water, agriculture, and fuel production. The carbon dioxide in the Martian atmosphere can also be converted into oxygen for breathing and as a propellant for rockets. In addition to water and carbon dioxide, Mars also has other valuable resources such as metals and minerals. These resources could be mined and processed to support the construction and maintenance of the colony. The ability to extract and utilize local resources would reduce the need for continuous resupply missions from Earth, making the colony more self-sufficient and sustainable. 10.1.5 Scientific research and exploration. Beyond the challenges of colonization, Mars offers a unique opportunity for scientific research and exploration. The planet's geological features, such as its ancient riverbeds and polar ice caps, provide valuable insights into the history and evolution of our solar system. By studying Mars, scientists can gain a better understanding of Earth's own past and the potential for life on other planets. Furthermore, Mars serves as a potential launchpad for further exploration of the solar system. Its proximity to the asteroid belt and the outer planets makes it an ideal base for future missions to explore and study these celestial bodies. By establishing a colony on Mars, humanity would be taking a significant step towards becoming an interplanetary species. 10.1.6 Ethical considerations. As we embark on the journey of Mars colonization, it is essential to consider the ethical implications of our actions. One of the primary concerns is planetary protection and the prevention of contamination. Mars may have the potential for microbial life, and any human presence could introduce Earth organisms that could harm or contaminate the Martian environment. Strict protocols and measures must be put in place to ensure the preservation of Mars' pristine conditions and the avoidance of irreversible damage. Another ethical consideration is the ownership and use of Martian resources. As humans begin to exploit the resources of Mars, questions arise regarding who has the right to claim and utilize these resources. International agreements and frameworks will need to be established to govern the responsible and equitable use of Martian resources. 10.1.7 The future of Mars colonization. The colonization and settlement of Mars represent a significant milestone in human history. It is a testament to our curiosity, ingenuity, and desire to explore the unknown. While the challenges are immense, the potential benefits are equally significant. Mars colonization could pave the way for the colonization of other planets and the long-term survival of humanity beyond Earth. As technology continues to advance and our understanding of Mars deepens, the dream of a Martian colony becomes increasingly attainable. It will require international collaboration, innovative solutions, and a steadfast commitment to exploration and discovery. The future of Mars colonization holds the promise of a new chapter in human history, where the Red Planet becomes a second home for humanity. 10.2 Human missions to other planets. As humanity continues to push the boundaries of space exploration, the idea of sending humans to other planets beyond Mars is becoming a topic of great interest and speculation. While Mars has been the primary focus of human missions in recent years, scientists and space agencies are already contemplating the possibility of sending astronauts to other planets in our solar system, such as Venus, Jupiter's moon Europa, and Saturn's moon Titan. These potential missions to other planets hold immense scientific and exploratory value, as well as the potential for expanding human presence in the cosmos. 10.2.1 Venus, Earth's evil twin. Venus, often referred to as Earth's evil twin, is the closest planet to Earth in terms of size and composition. Despite its inhospitable conditions, including a thick atmosphere of carbon dioxide and extreme temperatures, scientists believe that Venus may have had a more Earth-like environment in its distant past. Exploring Venus would provide valuable insights into the processes that shaped our own planet and could help us better understand the potential for habitability on other worlds. A human mission to Venus would face numerous challenges. The extreme temperatures, which can reach up to 900 degrees Fahrenheit, 475 degrees Celsius, would require advanced heat-resistant materials and cooling systems to protect astronauts and equipment. The dense atmosphere would also pose challenges for landing and takeoff, requiring innovative technologies for descent and ascent. Additionally, the corrosive nature of Venus's atmosphere would necessitate the development of durable and resilient spacecraft and spacesuits. Despite these challenges, a human mission to Venus could involve orbiters, landers, and even floating habitats in the planet's upper atmosphere. Scientists could study the planet's geology, atmosphere, and potential signs of past or present life. The mission could also provide valuable data on the effects of long-duration space travel on the human body, as astronauts would be exposed to high levels of radiation and extreme temperatures. 10.2.2 Europa, a moon of mysteries. Jupiter's moon Europa has long fascinated scientists due to its subsurface ocean, which is believed to contain more than twice the amount of water found on Earth. This vast ocean, kept in a liquid state by tidal forces from Jupiter's gravity, makes Europa one of the most promising candidates for extraterrestrial life in our solar system. A human mission to Europa would be a groundbreaking endeavor, allowing scientists to directly explore this icy moon and search for signs of life. The challenges of a human mission to Europa are numerous. The journey to Jupiter's vicinity would require advanced propulsion systems capable of traversing the vast distances of space. Once in orbit around Jupiter, a lander or a probe would need to be deployed to descend through Europa's thick ice crust and reach the subsurface ocean. This would require innovative drilling and sampling technologies to penetrate the icy surface and explore the potentially habitable environment below. Exploring Europa's subsurface ocean would provide invaluable insights into the potential for life beyond Earth. Scientists could study the composition of the water, search for organic molecules, and investigate the presence of hydrothermal vents that could support microbial life. Additionally, the mission could shed light on the moon's geology, its interaction with Jupiter's magnetic field, and the processes that shape its icy surface. 10.2.3 Titan, a world of possibilities. Saturn's moon Titan is a unique and intriguing destination for human missions. It is the only moon in our solar system with a dense atmosphere, composed primarily of nitrogen, with traces of methane and other organic compounds. Titan's atmosphere and surface conditions resemble those of early Earth, making it a potential laboratory for studying the origins of life and the processes that shaped our own planet. A human mission to Titan would face significant challenges. The journey to Saturn's vicinity would require advanced propulsion systems capable of reaching the outer reaches of our solar system. Once in orbit around Saturn, a lander or a probe would need to be deployed to descend through Titan's thick atmosphere and reach the surface. This would require innovative aerodynamic designs and parachutes to slow down the descent and ensure a safe landing. Exploring Titan's surface would provide unique insights into the chemistry and geology of this moon. Scientists could study the lakes and rivers of liquid methane and ethane, investigate the presence of organic molecules, and search for signs of prebiotic chemistry. The mission could also involve the deployment of rovers or even submarines to explore the methane lakes and potentially discover new forms of life or habitable environments. 10.2.4 Challenges and considerations. While the idea of human missions to other planets is exciting, it is important to acknowledge the numerous challenges and considerations involved. The technological advancements required for such missions would be unprecedented, requiring breakthroughs in propulsion systems, life support systems, radiation protection, and landing technologies. The long-duration nature of these missions would also pose significant physical and psychological challenges for astronauts, necessitating extensive research and preparation. Furthermore, the ethical and legal considerations surrounding human missions to other planets would need to be carefully addressed. Planetary protection protocols would be crucial to prevent contamination of potentially habitable environments with Earth organisms. The ownership and use of resources on other planets would also need to be defined to ensure fair and responsible exploration. International collaboration would be essential for the success of human missions to other planets. The pooling of resources, expertise, and funding from multiple nations would not only enhance the scientific value of these missions but also foster cooperation and peaceful exploration of space. In conclusion, while Mars has been the primary focus of human missions in recent years, the prospect of sending astronauts to other planets in our solar system holds immense scientific and exploratory potential. Venus, Europa, and Titan are just a few examples of destinations that could provide valuable insights into the origins of life, the processes that shape planetary bodies, and the potential for habitability beyond Earth. However, these missions would require significant technological advancements, careful planning, and international collaboration to overcome the challenges and ensure the responsible exploration of other worlds. 10.3 Advancements in Space Technology. Advancements in space technology have played a crucial role in enabling human missions to Mars and will continue to shape the future of Mars exploration. Over the years, scientists, engineers, and researchers have made significant progress in developing innovative technologies that have revolutionized space travel and made missions to Mars a reality. These advancements have not only improved the safety and efficiency of space missions but have also expanded our understanding of the Martian environment and the potential for human habitation on the Red Planet. 10.3.1 Propulsion Systems. One of the key areas of advancement in space technology is the development of propulsion systems for interplanetary travel. Traditional chemical propulsion systems, such as liquid and solid rocket engines, have been used for launching spacecraft into space and for initial stages of interplanetary missions. However, these systems have limitations in terms of fuel efficiency and the ability to carry heavy payloads over long distances. To overcome these limitations, scientists have been exploring alternative propulsion technologies, such as ion propulsion and nuclear propulsion. Ion propulsion systems use electric fields to accelerate ions and generate thrust, providing a more efficient and long-lasting propulsion method. Nuclear propulsion, on the other hand, utilizes the energy released from nuclear reactions to propel spacecraft at high speeds, significantly reducing travel time to Mars. 10.3.2 Life Support Systems. Another critical area of advancement in space technology is the development of life support systems for long-duration missions. Life support systems are responsible for providing astronauts with the necessary resources, such as air, water, and food, to survive in the harsh environment of space and on Mars. Innovations in life support systems have focused on improving efficiency, reliability, and sustainability. Advanced recycling systems have been developed to minimize water and waste generation, ensuring the efficient use of resources during long-duration missions. Additionally, advancements in food production technologies, such as hydroponics and aeroponics, have enabled astronauts to grow fresh food in space, reducing the reliance on resupply missions from Earth. 10.3.3 Robotics and Automation. Robotic exploration of Mars has been instrumental in gathering valuable data about the planet's geology, atmosphere, and potential for life. Advancements in robotics and automation have allowed scientists to design and deploy sophisticated rovers and landers capable of conducting complex experiments and observations on the Martian surface. The development of autonomous systems has enabled these robots to navigate challenging terrains, collect samples, and analyze them on-site. This has significantly increased the efficiency and productivity of Mars missions, as robots can perform tasks that would otherwise be time-consuming and risky for human astronauts. Furthermore, advancements in artificial intelligence and machine learning have enhanced the capabilities of these robots, enabling them to make real-time decisions and adapt to changing environments. 10.3.4 In situ resource utilization. In situ resource utilization (ISRU) is a key concept in future Mars missions, aiming to utilize local resources to sustain human presence on the planet. Advancements in space technology have made it possible to extract and utilize resources available on Mars, such as water ice, regolith, and carbon dioxide. ISRU technologies have been developed to extract water from Martian ice deposits, which can be used for drinking, growing plants, and producing rocket propellant. Additionally, regolith, the Martian soil, can be processed to extract valuable minerals and metals for construction and manufacturing purposes. These advancements in ISRU not only reduce the dependency on Earth for essential resources but also pave the way for long-term human habitation and colonization of Mars. 10.3.5 Communication and Navigation Systems. Communication and navigation systems are vital for the success of Mars missions, enabling real-time communication between astronauts and mission control on Earth and ensuring accurate navigation to and from the Red Planet. Advancements in space technology have led to the development of more robust and efficient communication and navigation systems. Satellite networks in space, such as the Mars Relay Network, have been established to provide continuous communication coverage between Mars and Earth. These networks use advanced communication protocols and high-gain antennas to transmit and receive data over long distances. Furthermore, advancements in navigation systems, such as the Global Positioning System (GPS), have improved the accuracy of spacecraft navigation, enabling precise landing on Mars and efficient trajectory planning. 10.3.6 Planetary Protection and Contamination Prevention. As human missions to Mars become a reality, the issue of planetary protection and contamination prevention has gained significant attention. Advancements in space technology have led to the development of stringent protocols and procedures to ensure that spacecraft and astronauts do not contaminate the Martian environment with Earth's microorganisms. Specialized cleanrooms and sterilization techniques have been developed to ensure that spacecraft are free from biological contaminants before launch. Additionally, strict quarantine measures are implemented for returning astronauts and samples to prevent any potential contamination of Earth's biosphere. These advancements in planetary protection and contamination prevention are crucial to preserve the integrity of Mars as a scientific and potentially habitable environment. In conclusion, advancements in space technology have been instrumental in enabling human missions to Mars and will continue to shape the future of Mars exploration. From propulsion systems and life support systems to robotics and automation, these advancements have improved the safety, efficiency, and sustainability of space missions. Furthermore, advancements in communication and navigation systems, as well as planetary protection and contamination prevention, have ensured the success and integrity of Mars missions. As we continue to push the boundaries of space exploration, further advancements in technology will undoubtedly unlock new possibilities for the exploration and colonization of Mars and other celestial bodies in our solar system. 10.4 International collaboration in Mars missions. International collaboration plays a crucial role in the exploration and colonization of Mars. The challenges and complexities of a Mars mission require the pooling of resources, expertise, and technology from multiple nations. Cooperation among countries not only enhances the scientific and technological capabilities but also promotes global unity and shared responsibility in the pursuit of space exploration. 10.4.1 History of international collaboration in Mars missions. The exploration of Mars has a long history of international collaboration. The first successful mission to Mars, the Mariner 4, was launched by the United States in 1964. Since then, numerous countries have joined forces to explore the Red Planet. The Soviet Union, now Russia, made significant contributions with its Mars program, including the successful Mars missions such as Mars 3 and Mars 6. In recent years, international collaboration in Mars missions has become more prevalent. The European Space Agency (ESA) has been actively involved in Mars exploration through its Mars Express mission, which has provided valuable data on the planet's atmosphere and surface. The ESA has also collaborated with Russia on the ExoMars mission, aiming to search for signs of past or present life on Mars. NASA, the United States Space Agency, has been at the forefront of Mars exploration. It has collaborated with various countries, including Canada, Japan, and European nations, on missions such as the Mars Science Laboratory (MSL) and the upcoming Mars Sample Return mission. These collaborations have allowed for the sharing of expertise, technology, and financial resources, making the missions more robust and successful. 10.4.2 Benefits of international collaboration. International collaboration brings several benefits to Mars missions. Firstly, it allows for the sharing of costs and resources, making ambitious missions more feasible. Mars missions require significant financial investments, and by pooling resources, countries can share the burden and achieve more together than they could individually. Secondly, collaboration enables the exchange of knowledge and expertise. Each country brings its unique strengths and capabilities to the table, and by working together, they can leverage their collective knowledge to overcome challenges and make scientific breakthroughs. Collaboration also fosters innovation, as different perspectives and approaches can lead to new ideas and solutions. Furthermore, international collaboration promotes diplomatic relations and strengthens global partnerships. Space exploration is a shared endeavor that transcends national boundaries, and by working together, countries can build trust, understanding, and cooperation. Collaborative missions also provide opportunities for cultural exchange and the development of long-lasting relationships between scientists, engineers, and astronauts from different nations. 10.4.3 Examples of international collaboration in Mars missions. One notable example of international collaboration in Mars missions is the International Mars Exploration Working Group, IMEWG. The IMEWG is a forum where space agencies from around the world come together to discuss and coordinate their Mars exploration efforts. It serves as a platform for sharing information, coordinating mission plans, and identifying areas of collaboration. Another example is the Mars Sample Return mission, a joint effort between NASA and the ESA. This ambitious mission aims to collect samples from the Martian surface and return them to Earth for detailed analysis. The collaboration between the two agencies allows for the sharing of expertise in sample collection, spacecraft design, and mission planning, making the mission more efficient and effective. Additionally, the Mars Society, a nonprofit organization dedicated to the exploration and settlement of Mars, has been instrumental in promoting international collaboration. The Society organizes conferences, workshops, and simulations that bring together scientists, engineers, and enthusiasts from different countries to exchange ideas and collaborate on Mars-related projects. 10.4.4 Challenges and considerations in international collaboration. While international collaboration in Mars missions brings numerous benefits, it also presents challenges and considerations. One of the main challenges is the coordination of different national interests, priorities, and funding mechanisms. Each country has its own goals and objectives, and finding common ground can be a complex process. Effective communication, negotiation, and compromise are essential to ensure the success of collaborative missions. Another consideration is the legal and regulatory framework governing international space cooperation. Issues such as intellectual property rights, data sharing, and liability for mission failures need to be addressed to facilitate smooth collaboration. International agreements and treaties, such as the Outer Space Treaty, provide a foundation for cooperation but may require further refinement to accommodate the complexities of Mars missions. Furthermore, cultural and language barriers can pose challenges in international collaboration. Different countries have their own working styles, communication norms, and decision-making processes. Building effective cross-cultural teams and fostering a spirit of inclusivity and respect are crucial for successful collaboration. 10.4.5 Future Prospects for International Collaboration. The future of Mars exploration holds great potential for increased international collaboration. As more countries develop their space programs and express interest in Mars missions, the opportunities for collaboration will expand. The establishment of a sustained human presence on Mars will likely require a global effort, with countries contributing their expertise and resources to ensure the success of long-duration missions. International collaboration can also extend beyond government agencies to include private companies and academic institutions. The emergence of commercial space companies, such as SpaceX and Blue Origin, has brought new players into the field, offering innovative approaches and technologies. Collaborations between government agencies, private companies, and academic institutions can leverage the strengths of each sector and accelerate progress in Mars exploration. In conclusion, international collaboration is essential for the success of Mars missions. By pooling resources, expertise, and technology, countries can overcome the challenges of Mars exploration and achieve scientific breakthroughs. Collaboration promotes global unity, shared responsibility, and the advancement of space exploration for the benefit of all humankind. 11. Ethical and legal considerations. 11.1 Planetary protection and contamination. As humanity sets its sights on Mars, one of the most critical considerations is the concept of planetary protection and contamination. Planetary protection refers to the measures taken to prevent the contamination of other celestial bodies with Earth's microorganisms and to protect Earth from potential extraterrestrial life. This is of utmost importance in order to preserve the integrity of scientific exploration and to avoid any unintended consequences that could arise from the introduction of foreign organisms to Mars. 11.1.1 The importance of planetary protection. The exploration of Mars holds great scientific value, as it provides us with a unique opportunity to study the potential for life beyond Earth. By ensuring that our missions to Mars are conducted with strict adherence to planetary protection protocols, we can preserve the pristine nature of the Martian environment and avoid any contamination that could compromise future scientific discoveries. One of the primary reasons for implementing planetary protection measures is the possibility of finding evidence of past or present life on Mars. If we were to introduce Earth's microorganisms to the Martian surface, it would be nearly impossible to distinguish between indigenous Martian life and the organisms we brought with us. This could lead to false conclusions and hinder our understanding of the true nature of Mars. Furthermore, the concept of planetary protection is not only about preserving scientific integrity but also about ethical considerations. Just as we have a responsibility to protect our own planet's ecosystems, we must extend that responsibility to other celestial bodies. Mars, with its potential for harboring life, deserves our utmost respect and caution. 11.1.2 Preventing contamination. To prevent contamination, space agencies and mission planners have developed strict protocols and guidelines. These protocols are designed to minimize the likelihood of introducing Earth's microorganisms to Mars and to ensure that any potential Martian samples returned to Earth are handled with the utmost care. One of the key aspects of preventing contamination is the sterilization of spacecraft and equipment before they are sent to Mars. This involves subjecting the hardware to rigorous cleaning procedures and sterilization techniques to eliminate any potential microbial hitchhikers. Additionally, spacecraft are assembled in clean rooms to minimize the introduction of contaminants during the manufacturing process. Another important aspect of preventing contamination is the selection of landing sites. Mission planners carefully choose landing sites that have a low probability of containing potential habitats for life. By avoiding areas that may have liquid water or other conditions conducive to life, the risk of contamination is significantly reduced. 11.1.3 Sample return missions and containment. Sample return missions, which involve bringing Martian samples back to Earth for detailed analysis, present a unique challenge in terms of planetary protection. The utmost care must be taken to ensure that any potential Martian organisms or organic material are contained and do not pose a risk to Earth's biosphere. To address this challenge, sample return missions are subject to stringent containment protocols. The samples are carefully collected and stored in sealed containers that are designed to prevent any potential contamination from escaping. These containers are then transported back to Earth under controlled conditions, with multiple layers of containment to minimize the risk of release. Upon arrival on Earth, the samples are handled in specialized laboratories that are equipped with strict containment facilities. Scientists and researchers follow strict protocols to prevent any potential contamination and to ensure the safety of both the samples and the environment. 11.1.4 International cooperation and planetary protection. Planetary protection is not a concern limited to a single nation or space agency. It is a global responsibility that requires international cooperation and collaboration. The international community has recognized the importance of planetary protection and has established guidelines and agreements to ensure that all nations adhere to the same standards. The Committee on Space Research (COSPAR) plays a crucial role in developing and maintaining planetary protection guidelines. COSPAR's planetary protection policy is widely accepted and followed by space agencies around the world. This policy provides a framework for the implementation of planetary protection measures and promotes the exchange of information and best practices among nations. International cooperation in planetary protection is essential to ensure that all missions to Mars, regardless of their origin, adhere to the same high standards. By working together, we can collectively safeguard the integrity of Mars and protect the potential for scientific discoveries that lie within its ancient landscapes. Conclusion. Planetary protection and contamination are critical considerations in the exploration of Mars. By implementing strict protocols and guidelines, we can ensure the preservation of the Martian environment and the integrity of scientific exploration. The importance of planetary protection extends beyond scientific value. It is a matter of ethical responsibility and global cooperation. As we venture further into the cosmos, it is imperative that we continue to prioritize the protection of celestial bodies and the preservation of their unique ecosystems. 11.2 Ownership and use of Martian resources. As humanity sets its sights on Mars, the question of ownership and use of Martian resources becomes a crucial consideration. With the potential for valuable resources such as water, minerals, and even potential energy sources, it is important to establish a framework for the responsible and equitable utilization of these resources. 11.2.1 Resource potential of Mars. Mars is a planet rich in resources that could be of great value to future human missions and potential colonization efforts. One of the most significant resources on Mars is water, which exists in the form of ice in the polar regions and possibly underground. Water is essential for sustaining life, providing drinking water, growing crops, and producing rocket propellant through electrolysis. Additionally, Mars is believed to have abundant mineral resources, including iron, aluminum, silicon, and sulfur, which could be used for construction and manufacturing purposes. The planet's regolith, or surface material, may also contain valuable elements such as platinum, gold, and rare earth metals. Furthermore, Mars has an atmosphere that is predominantly composed of carbon dioxide, which could potentially be utilized for the production of breathable air and as a source of carbon for manufacturing processes. 11.2.2 International cooperation and treaties. Given the global nature of space exploration, it is essential to establish a framework for international cooperation and collaboration in the ownership and use of Martian resources. The Outer Space Treaty, which was signed by many countries, including major spacefaring nations, serves as the foundation for governing space activities. According to the treaty, celestial bodies, including Mars, are considered the common heritage of mankind, and no nation can claim sovereignty over them. This principle ensures that Mars and its resources are accessible to all nations for peaceful purposes and prohibits any form of national appropriation. 11.2.3 Property rights and commercial exploitation. While the Outer Space Treaty prohibits national ownership of celestial bodies, it does not explicitly address the issue of private ownership or commercial exploitation of resources. This has led to debates and discussions regarding the establishment of property rights on Mars. Some argue that the first entity or nation to establish a presence on Mars should have the right to claim and exploit resources. Others advocate for a more collaborative approach, suggesting the creation of an international framework that allows for the equitable distribution and utilization of Martian resources. In recent years, there have been initiatives to address this issue. For example, the United States passed the Commercial Space Launch Competitiveness Act in 2015, which grants private companies the rights to resources they extract from celestial bodies, including Mars. However, this legislation has been met with criticism from other nations, as it appears to contradict the principles of the Outer Space Treaty. 11.2.4 Ethical considerations. The ownership and use of Martian resources raise important ethical considerations. As humans venture to Mars, it is crucial to ensure that the exploitation of resources is done in a manner that is sustainable and respects the Martian environment. This includes minimizing the impact on the planet's delicate ecosystems and preserving its geological features for scientific study. Additionally, the rights and well-being of any potential indigenous life, such as microbial organisms, must be taken into account. The principle of planetary protection, which aims to prevent contamination of celestial bodies with Earth's microorganisms, plays a significant role in guiding ethical practices in space exploration. 11.2.5 Future frameworks and regulations. As the exploration and potential colonization of Mars become a reality, there is a need for the development of clear frameworks and regulations regarding the ownership and use of Martian resources. International collaboration and dialogue will be crucial in establishing these frameworks to ensure fairness, sustainability, and adherence to ethical principles. It is likely that future treaties and agreements will be necessary to address the complexities of resource utilization on Mars and to provide a legal framework for private and commercial entities operating on the planet. In conclusion, the ownership and use of Martian resources present complex challenges that require careful consideration. International cooperation, adherence to existing treaties, and the establishment of new frameworks and regulations will be essential in ensuring the responsible and equitable utilization of these resources. As humanity embarks on its mission to Mars, it is crucial to strike a balance between scientific exploration, commercial interests, and ethical considerations to ensure a sustainable and prosperous future for both Earth and Mars. 11.3 Human rights and responsibilities in space. As humanity embarks on the ambitious mission to explore and colonize Mars, it is crucial to consider the ethical and legal implications of our actions in space. The concept of human rights and responsibilities extends beyond the boundaries of Earth and must be upheld even in the vastness of space. In this chapter, we will delve into the various aspects of human rights and responsibilities in space exploration, particularly in the context of Mars missions. 11.3.1 Ensuring the rights of astronauts. The rights of astronauts are of paramount importance in any space mission, including those to Mars. As individuals who willingly venture into the unknown, astronauts must be provided with a safe and healthy environment, both physically and mentally. This includes ensuring their physical well-being through proper medical care, nutrition, and exercise, as well as addressing their psychological needs through adequate support systems and communication with loved ones back on Earth. Furthermore, astronauts should be granted the right to privacy and personal autonomy, even in the confined spaces of a spacecraft or Martian habitat. They should have the freedom to express their thoughts and emotions without fear of reprisal, and their personal data and communications should be protected from unauthorized access. 11.3.2 Equality and diversity in space. In the spirit of equality and inclusivity, it is essential to promote diversity in space exploration. Mars missions should strive to include individuals from different backgrounds, cultures, and genders, ensuring equal opportunities for all. By embracing diversity, we can harness the collective knowledge and experiences of a wide range of individuals, fostering innovation and creativity in our quest to explore the Red Planet. Furthermore, it is crucial to address any potential discrimination or bias that may arise during space missions. Strict protocols and guidelines should be in place to prevent any form of discrimination based on race, gender, religion, or any other characteristic. By fostering an environment of respect and inclusivity, we can create a harmonious and productive atmosphere for all astronauts involved in Mars missions. 11.3.3 Environmental responsibility. As we venture into space, we must also consider our responsibility towards the Martian environment. Mars, with its unique geological features and potential for life, should be treated with the utmost respect and care. Any activities conducted on the Martian surface should be done in a manner that minimizes environmental impact and preserves the planet's natural resources. Strict protocols should be in place to prevent contamination of Mars with earthly organisms, ensuring the preservation of any potential indigenous life forms. Planetary protection measures should be implemented to prevent the introduction of harmful substances or microorganisms that could disrupt the delicate balance of the Martian ecosystem. Additionally, efforts should be made to minimize waste generation and develop sustainable practices for resource utilization on Mars. Recycling and reusing materials, as well as exploring methods for utilizing local resources, can help reduce the reliance on Earth for supplies and minimize the ecological footprint of Mars missions. 11.3.4 International cooperation and collaboration. The exploration and colonization of Mars should not be seen as a competition among nations but rather as a collaborative effort for the benefit of all humanity. International cooperation is crucial in ensuring the success and sustainability of Mars missions. By sharing knowledge, resources, and expertise, nations can pool their efforts to overcome the challenges of space exploration and maximize the potential for scientific discoveries. International agreements and treaties should be established to govern the ethical and legal aspects of Mars missions. These agreements should address issues such as the sharing of scientific data, intellectual property rights, and the fair distribution of resources obtained from Mars. By establishing a framework of cooperation and mutual respect, we can ensure that the exploration and utilization of Mars are conducted in a manner that benefits all nations and respects the rights of all involved. In conclusion, as we embark on the mission to explore and colonize Mars, it is imperative to uphold human rights and responsibilities in space. Astronauts must be provided with a safe and healthy environment, diversity and equality should be promoted, environmental responsibility must be prioritized, and international cooperation should be fostered. By adhering to these principles, we can ensure that our journey to Mars is not only scientifically fruitful but also ethically and morally sound. 11.4 Environmental impact of Mars missions. As humanity sets its sights on Mars, it is crucial to consider the potential environmental impact of our missions to the Red Planet. While Mars may seem like an uninhabited and desolate world, it is essential to remember that any human presence on Mars will have consequences for the planet's delicate ecosystem. In this section, we will explore the potential environmental impact of Mars missions and the steps that can be taken to mitigate any negative effects. 11.4.1 Planetary protection and contamination. One of the primary concerns when it comes to Mars missions is the concept of planetary protection. Planetary protection refers to the measures taken to prevent the contamination of Mars with Earth organisms and vice versa. The goal is to preserve the pristine nature of Mars for scientific exploration and to avoid any potential harm to indigenous Martian life, if it exists. To ensure planetary protection, strict protocols are followed during the design and construction of spacecraft and landers. These protocols include sterilization procedures to minimize the chance of introducing Earth microbes to Mars. Additionally, landing sites are carefully selected to minimize the risk of contamination, especially in areas where signs of potential life or water have been detected. 11.4.2 Habitat design and construction. The construction of habitats on Mars will also have an environmental impact. To create a sustainable living environment for astronauts, habitats will need to be built using local resources, such as Martian soil and rocks. This approach will reduce the need to transport construction materials from Earth, minimizing the carbon footprint of the mission. However, it is crucial to ensure that the extraction and use of Martian resources are done in an environmentally responsible manner. Careful consideration must be given to the long-term effects of resource extraction on the Martian environment, including potential changes to the landscape and the impact on any existing Martian life. 11.4.3 Energy and Resource Management. Energy and resource management will be critical on Mars to minimize the environmental impact of human activities. Mars missions will likely rely on renewable energy sources, such as solar power, to meet the energy needs of the astronauts and their equipment. This approach will reduce the reliance on fossil fuels and minimize greenhouse gas emissions. Efficient resource management will also be essential to ensure the sustainability of Mars missions. Recycling and reusing resources, such as water and waste, will be crucial to minimize the need for resupply missions from Earth. Additionally, technologies for extracting and utilizing Martian resources, such as water, ice and minerals, will need to be developed and implemented in an environmentally responsible manner. 11.4.4 Waste Management and Pollution Control. Proper waste management and pollution control will be vital to prevent the accumulation of waste and the release of harmful substances into the Martian environment. Advanced waste recycling systems will need to be developed to minimize the generation of waste and to recycle as much as possible. To prevent pollution, strict protocols will be in place to ensure that hazardous materials are handled and stored safely. Any potential pollutants, such as chemicals or radioactive materials, must be carefully managed to prevent contamination of the Martian environment. 11.4.5 Long-term environmental monitoring. To understand the long-term environmental impact of Mars missions, continuous monitoring of the Martian environment will be necessary. This monitoring will involve studying the changes in the atmosphere, climate, and geological features of Mars over time. Robotic missions and remote sensing technologies will play a crucial role in collecting data and monitoring the Martian environment. This information will help scientists and engineers assess the impact of human activities on Mars and make informed decisions to mitigate any negative effects. 11.4.6 Mitigating environmental impact. To minimize the environmental impact of Mars missions, it is essential to prioritize sustainability and environmental stewardship. This can be achieved through research and development of environmentally friendly technologies and practices, collaboration between international space agencies to share knowledge and resources, strict adherence to planetary protection protocols to prevent contamination, long-term monitoring and assessment of the Martian environment, education and awareness programs to promote environmental responsibility among astronauts and mission personnel. By taking these measures, we can ensure that our exploration and colonization of Mars are conducted in a way that respects and preserves the planet's unique environment. It is our responsibility to be good stewards of Mars and to ensure that future generations can continue to explore and learn from this fascinating world. 12. Conclusion. 12.1 Summary of Mars exploration. Mars, the fourth planet from the Sun, has captivated the imagination of scientists and space enthusiasts for centuries. Over the years, numerous missions have been launched to explore the Red Planet, each contributing valuable knowledge and paving the way for future endeavors. In this section, we will summarize the key findings and achievements of Mars exploration, highlighting the significant milestones and discoveries that have shaped our understanding of this enigmatic world. 12.1.1 Early exploration. The exploration of Mars began with early observations from Earth, where astronomers observed its distinct reddish hue and observed its motion across the night sky. However, it wasn't until the 1960s that the first successful missions were launched to study Mars up close. The Mariner program, initiated by NASA, sent a series of robotic spacecraft to fly by and photograph the planet, providing the first close-up images of its surface and revealing its intriguing geological features. 12.1.2 Viking missions. One of the most significant milestones in Mars exploration was the Viking program, which consisted of 2 landers and 2 orbiters launched by NASA in the 1970s. These missions aimed to search for signs of life on Mars by studying its soil and atmosphere. The landers successfully touched down on the Martian surface, conducting experiments to analyze the soil composition and search for organic molecules. Although the results were inconclusive regarding the presence of life, the Viking missions provided valuable insights into the planet's geology and atmospheric conditions. 12.1.3 Mars rovers. The next major leap in Mars exploration came with the deployment of rovers on the planet's surface. The Sojourner rover, part of the Mars Pathfinder mission in 1997, was the first successful mobile robot to explore Mars. It provided scientists with detailed images and data about the Martian surface, including evidence of past water activity. Building on this success, subsequent missions such as the Mars exploration rovers Spirit and Opportunity, and later the Curiosity rover, further expanded our knowledge of Mars geology, climate, and potential for habitability. 12.1.4 Recent missions and discoveries. In recent years, several missions have continued to unravel the mysteries of Mars. The Mars Science Laboratory mission, which carried the Curiosity rover, made significant discoveries, including the detection of organic compounds and the confirmation of a habitable environment in the planet's past. The InSight mission, launched in 2018, focused on studying the planet's interior, providing valuable insights into its seismic activity and internal structure. Additionally, the Mars Atmosphere and Volatile Evolution (MAVEN) mission has been studying the Martian atmosphere, shedding light on its history and the processes that led to its current state. The ExoMars mission, a collaboration between the European Space Agency (ESA) and Roscosmos, aims to search for signs of past or present life on Mars, with future missions planned to drill beneath the surface to search for evidence of microbial life. 12.1.5 Key Findings and Achievements. Through these missions, scientists have made significant discoveries that have reshaped our understanding of Mars. The presence of water in the form of ice, evidence of ancient riverbeds, and the identification of minerals that require liquid water for their formation all point to the possibility that Mars once had a more hospitable environment for life. The detection of methane in the Martian atmosphere has also sparked excitement, as it could be a potential indicator of biological activity. Furthermore, the exploration of Mars has provided valuable insights into the challenges humans would face during a manned mission to the planet. Understanding the planet's harsh climate, radiation levels, and the need for life support systems has been crucial in planning future missions and ensuring the safety and well-being of astronauts. 12.1.6 Looking ahead. As we reflect on the accomplishments of Mars exploration, it is clear that our journey has only just begun. The knowledge gained from these missions has laid the foundation for future endeavors, including the ambitious goal of sending humans to Mars. The challenges that lie ahead are immense, from developing advanced propulsion systems to ensuring the long-term sustainability of human presence on the planet. However, the potential rewards, both scientific and inspirational, make the pursuit of Mars exploration a worthy endeavor. In conclusion, Mars exploration has been a remarkable journey of discovery and innovation. From early observations to the deployment of rovers and landers, each mission has contributed to our understanding of Mars' geology, climate, and potential for life. The findings and achievements have not only expanded our knowledge of the Red Planet but have also inspired future generations of explorers to continue pushing the boundaries of human exploration. As we look to the future, the exploration of Mars holds the promise of unlocking the secrets of our neighboring planet and perhaps even answering the age-old question, are we alone in the universe? 12.2 Lessons Learned and Future Prospects. As we conclude our exploration of Mars and the mission Red Planet, it is important to reflect on the lessons we have learned and consider the future prospects of Mars exploration. The journey to Mars has been a monumental undertaking, pushing the boundaries of human knowledge and technological capabilities. Throughout this mission, we have encountered numerous challenges and made significant advancements, paving the way for future missions and the potential colonization of Mars. 12.2.1 Lessons Learned. One of the most important lessons we have learned from the mission Red Planet is the significance of meticulous mission planning. The success of any Mars mission relies heavily on thorough preparation, including the selection and training of astronauts, the design of spacecraft and technology, and the careful consideration of potential risks and challenges. The mission Red Planet has demonstrated the importance of interdisciplinary collaboration and the need for comprehensive contingency plans to address unforeseen circumstances. Another crucial lesson learned is the importance of understanding the Martian environment. Through the exploration of Mars, we have gained valuable insights into the planet's geology, geography, atmosphere, and potential for life. These findings have not only expanded our knowledge of Mars but have also provided valuable information for future missions, enabling us to make informed decisions about landing sites, resource utilization, and habitat design. Furthermore, the mission Red Planet has highlighted the significance of sustainable living and resource management. The development of efficient life support systems, food production techniques, and water and waste management strategies has been essential for the long-duration missions to Mars. These lessons can be applied not only to future Mars missions but also to sustainable living practices on Earth. Additionally, the mission Red Planet has emphasized the importance of international collaboration in space exploration. The sharing of resources, expertise, and technological advancements among different nations has been instrumental in the success of the mission. Collaborative efforts have not only reduced costs but have also fostered a sense of unity and cooperation among nations, paving the way for future joint missions and the establishment of international space exploration frameworks. 12.2.2 Future Prospects. Looking ahead, the future of Mars exploration holds immense potential. The knowledge and experience gained from the mission Red Planet will serve as a foundation for future missions, enabling us to overcome challenges and further expand our understanding of the Red Planet. Here are some of the future prospects for Mars exploration. 12.2.2.1 Advancements in Technology. The rapid advancements in technology will play a crucial role in the future of Mars exploration. From improved propulsion systems for faster interplanetary travel to more efficient life support systems and communication and navigation technologies, these advancements will enhance the safety, efficiency, and sustainability of future missions. Furthermore, the development of robotics and artificial intelligence will enable more extensive and precise exploration of Mars, allowing us to gather valuable data and conduct experiments remotely. 12.2.2.2 Human colonization. The ultimate goal of Mars exploration is the colonization and establishment of a sustainable human presence on the planet. The lessons learned from the mission Red Planet will guide future colonization efforts, ensuring the safety and well-being of the colonists. The establishment of permanent habitats, resource utilization, and the development of self-sustaining ecosystems will be key areas of focus. Mars colonization will not only expand our horizons as a species but also serve as a stepping stone for future human missions to other planets. 12.2.2.3 Search for life. The search for life on Mars will continue to be a significant focus of future missions. The discoveries made during the mission Red Planet have provided tantalizing hints of the potential for past or present life on Mars. Future missions will employ more sophisticated instruments and techniques to further investigate these possibilities. The study of Martian geology, the search for water, and the analysis of the Martian atmosphere will provide valuable insights into the habitability of Mars and the potential for extraterrestrial life. 12.2.2.4 International collaboration. International collaboration will remain a crucial aspect of future Mars missions. The sharing of resources, expertise, and technological advancements among nations will not only reduce costs but also foster a sense of unity and cooperation in the exploration of Mars. Collaborative efforts will enable the pooling of knowledge and resources, leading to more ambitious missions and a deeper understanding of the Red Planet. In conclusion, the mission Red Planet has provided us with invaluable lessons and insights into Mars exploration. The meticulous planning, interdisciplinary collaboration, and technological advancements have paved the way for future missions and the potential colonization of Mars. The future prospects of Mars exploration are exciting, with advancements in technology, human colonization, the search for life, and international collaboration on the horizon. As we continue to explore the mysteries of Mars, we inspire the next generation of explorers to push the boundaries of human knowledge and embark on even more ambitious missions to the Red Planet. 12.3 Inspiring the next generation of explorers. As we conclude our journey through the exploration of Mars, it is important to reflect on the impact that this mission has had on inspiring the next generation of explorers. The quest to reach Mars has captured the imagination of people around the world, igniting a passion for space exploration and pushing the boundaries of human knowledge and capabilities. In this final section, we will explore the ways in which the mission Red Planet has inspired and will continue to inspire future generations of explorers. 12.3.1 The Power of Inspiration. The exploration of Mars has always been a symbol of human curiosity and the desire to push the limits of what is possible. The mission Red Planet has served as a beacon of hope and inspiration for aspiring scientists, engineers, and astronauts. The challenges and risks associated with a Mars mission have not deterred but rather motivated the next generation to dream big and pursue careers in space exploration. 12.3.2 Education and Outreach Programs. One of the key ways in which the mission Red Planet has inspired the next generation is through education and outreach programs. These programs aim to engage young minds in the wonders of space exploration and provide them with the knowledge and skills needed to pursue careers in the field. Through interactive workshops, summer camps, and school visits, children and teenagers are exposed to the excitement and possibilities of Mars exploration. 12.3.3 Role Models and Mentors. Another important aspect of inspiring the next generation of explorers is the presence of role models and mentors. Astronauts and scientists involved in the mission Red Planet serve as inspirational figures, sharing their experiences and knowledge with aspiring explorers. Through talks, interviews, and social media, these role models provide guidance and encouragement to young minds, showing them that their dreams of reaching Mars are within reach. 12.3.4 STEM Education and Mars Curriculum. The exploration of Mars has also had a significant impact on the field of STEM, science, technology, engineering, and mathematics education. The mission Red Planet has provided a real-world context for teaching these subjects, making them more engaging and relevant to students. Mars-themed curriculum and educational resources have been developed, allowing students to learn about various scientific and technological concepts while also fostering their interest in space exploration. 12.3.5 Citizen Science and Amateur Astronomy. The mission Red Planet has not only inspired future professionals but has also engaged amateur astronomers and citizen scientists. Through initiatives such as Mars observation campaigns and citizen science projects, individuals from all walks of life have been able to contribute to the exploration of Mars. By involving the public in the scientific process, the mission has fostered a sense of ownership and connection to the exploration of the Red Planet. 12.3.6 Advancements in Technology and Innovation. The technological advancements made during the mission Red Planet have also played a crucial role in inspiring the next generation of explorers. The development of new spacecraft, propulsion systems, and life support technologies has showcased the power of human ingenuity and innovation. These advancements have not only expanded our capabilities for Mars exploration but have also inspired young minds to pursue careers in engineering and technology. 12.3.7 Collaboration and International Cooperation. The mission Red Planet has demonstrated the importance of collaboration and international cooperation in achieving ambitious goals. The mission has brought together scientists, engineers, and astronauts from different countries, working towards a common objective. This spirit of collaboration has not only advanced our understanding of Mars but has also inspired future generations to embrace diversity and work together towards a shared vision. 12.3.8 The Future of Mars Exploration. As we look to the future, the mission Red Planet will continue to inspire the next generation of explorers. The advancements made during this mission will serve as a foundation for future Mars missions, pushing the boundaries of what is possible and inspiring new generations to dream big. The quest to reach Mars will remain a driving force for scientific discovery and human exploration, inspiring the next generation to continue the journey beyond our home planet. In conclusion, the mission Red Planet has served as a catalyst for inspiring the next generation of explorers. Through education, outreach programs, role models, and technological advancements, the mission has ignited a passion for space exploration and pushed the boundaries of human knowledge and capabilities. As we continue to explore the wonders of Mars and beyond, we must remember the importance of inspiring and nurturing the next generation of explorers who will carry the torch of discovery into the future. 12.4 Final Thoughts on Mission Red Planet. As we come to the end of this journey exploring the intricacies of a mission to Mars, it is important to reflect on the significance and impact of such an endeavor. Mission Red Planet represents the culmination of human ingenuity, determination, and the relentless pursuit of knowledge. It is a testament to our innate curiosity and our desire to push the boundaries of what is possible. 12.4.1 A bold step into the unknown. Embarking on a mission to Mars is not just a scientific endeavor, it is a testament to the human spirit of exploration. It represents our innate desire to venture into the unknown, to challenge ourselves, and to expand our horizons. Mission Red Planet is a bold step towards unraveling the mysteries of the Red Planet and understanding our place in the universe. 12.4.2 Advancing Science and Technology. The exploration of Mars has always been driven by the pursuit of scientific knowledge. Mission Red Planet has provided us with invaluable insights into the geology, climate, and potential for life on Mars. The data and samples collected during this mission will undoubtedly revolutionize our understanding of the Red Planet and contribute to advancements in various scientific disciplines. Moreover, the technological advancements made in the process of planning and executing Mission Red Planet have far-reaching implications. From spacecraft design and propulsion systems to life support and communication technologies, the innovations developed for this mission have the potential to revolutionize space exploration and benefit humanity as a whole. 12.4.3 Inspiring the Next Generation. Mission Red Planet has captured the imagination of people around the world, inspiring a new generation of explorers, scientists, and engineers. The audacity and ambition of this mission have ignited a spark in the hearts and minds of young individuals who dream of one day venturing beyond Earth's boundaries. It serves as a reminder that no dream is too big and that with dedication and perseverance, we can achieve the seemingly impossible. 12.4.4 Collaboration and Unity. One of the most remarkable aspects of Mission Red Planet is the international collaboration that made it possible. Scientists, engineers, and astronauts from different countries came together, pooling their expertise and resources to achieve a common goal. This mission exemplifies the power of collaboration and the potential that can be unlocked when nations unite for a shared purpose. 12.4.5 The Fragility of our Home Planet. Mission Red Planet also serves as a stark reminder of the fragility of our home planet, Earth. As we venture into the depths of space, we are confronted with the realization that our planet is a precious and delicate oasis in the vastness of the universe. The challenges and risks associated with a mission to Mars highlight the importance of preserving and protecting our own planet for future generations. 12.4.6 A Glimpse into the Future. Mission Red Planet is not just a singular event, it is a stepping stone towards a future where humans may one day call Mars their second home. The knowledge gained from this mission will pave the way for future colonization and settlement efforts, opening up new possibilities for humanity's expansion beyond Earth. It represents a glimpse into a future where interplanetary travel and exploration become a reality. 12.4.7 The Human Spirit of Exploration. In the end, Mission Red Planet is a testament to the indomitable human spirit of exploration. It is a reminder that we are a species driven by curiosity, innovation, and the desire to push the boundaries of what is possible. The challenges and risks associated with a mission to Mars are immense, but they pale in comparison to the potential rewards and the knowledge that awaits us. As we conclude this journey, let us remember that Mission Red Planet is not just about reaching Mars, it is about reaching for the stars. It is a symbol of our collective ambition, our thirst for knowledge, and our unwavering belief in the power of human ingenuity. May it inspire us to continue pushing the boundaries of exploration and to never stop dreaming of what lies beyond.